Okay, good morning, everyone. Welcome to the second day of the FAS's The Challenge of Megaconstellations webinar. We had some very good feedback for yesterday's talks, and I'm sure that today's talks are going to be excellent as well. For those of you who weren't here yesterday, the FAS is a UK organisation that supports UK astronomical societies. We have about 200 societies as our members, and therefore indirectly we provide support to between 12 and 13,000 amateur astronomers in the UK. I will repeat my comment yesterday that we have no formal code of conduct, but everyone is expected to behave professionally and be respectful, and you will be removed from the webinar if you're otherwise. Okay, so without further ado, if you're ready, I'm a little early, Olivier. I'll hand over to Olivier Hainaut, who's our first speaker for this morning.
Thank you, Paul. Well, okay. Thanks a lot for the invitation, and it's a pleasure and an honor to be among all the speakers. It's really fantastically interesting. So let me share my screen and get started. So first, sharing screen, share, and full screen. Full screen. Okay. Can you please confirm it is sharing properly?
Yes, we can see that, Olivier.
Excellent. Okay, so I'm going to talk about the effect of satellite constellation on astronomers. And in this first talk, I'm going to talk about about the number, the type of constellations that we can see. So this is a work that is done together with my colleagues at ESO and my co-authors on various papers. So it all started in May 19, and just like everybody else, we were surprised, and yeah, basically there was a whiff of panic. Is it really the end of astronomy as we see it? And when we got this kind of images from professional observatories, my organization, the European Southern Observatory, decided that it was worth evaluating in numbers what would be the effect on our telescopes. So the very, very large telescope that you see behind me and our fleet of telescopes, to see basically how our investment, your investment, would be affected, considering it's overall a billion euro machine. It's worth seeing how much we're going to lose. So in this first talk, I'm going to first talk about the geometry and what we see depending of the time of night, time of year, latitude, etc. I also mention things about naked eye observations. In a second talk that comes later, I will talk specifically about the impact on astronomical observations. So for this first talk, as I want to go really in numbers, we first need to know how many satellites are and will be in orbit. So this table on the left is a catalog of the constellations that for which we found information. So some of them have been launching already. Starlink has about 2,000 satellites. OneWeb has about 400, but there are many others to come. And if you look at the total, we're talking about 100,000 satellites. Some of these companies will collapse. Some of these companies will not launch. For example, Boeing and Leosat have withdrawn their applications. Others will come and replace them. So the actual details of this table are not too important. What is important is that it gives us a good idea of the type of population of satellites that we could have in let's say around 2030. So just a word on the satellite distribution. Most of these satellites are spread on Walker configuration. So here you have an example for one of the Starlink shells, which is about 1,000 satellites that are spread over many planes, and each plane is one of these blue lines. One of them is highlighted in red, and then the satellites are evenly spread over these lines. And one full constellation is made up of several of these shells. So if you go to this super cool website, satellite-map.space, you can see the distribution of the Starlinks in real time. And so you see all the dots represent a Starlink satellite in its position. And you see that there are some lines here. These are recently launched satellites that are still bunched together. They will slowly spread and take their place in the overall constellation. Okay, just a word on how we get our results. It's simulations. The first is really simple. We compute the position and the brightness of all the satellites, so 100,000. And then we project them on the sky and we count them. So this is basically just geometry. So there is no advanced physics in this. The problem is that it's kind of computer intensive to do it for so many satellites. So a colleague of mine, Kees Bassa, had a stroke of genius and found a function that analytically represents the distribution of satellites over a shell. And so that means that just by solving an equation, we can get the density of satellites. So we don't get little dots as in the numerical simulation, we get densities of satellites. The advantage is that it is lightning fast, so we can do really lots of simulations. And of course, we cross-validated our results together and with other people working on this kind of work. So let's start with the observability of the satellites. To be observable, a satellite must be above the horizon. And if you look at stars, you see about half the stars above the horizon and half the stars are below the horizon. For satellites, it's more complicated because they are so nearby that you see only a fraction. And so in this figure, you see a constellation side view, front view. The Earth is the black circle. The observatory would be the black dot at the top, and I marked the local horizon with a black line. So that means that from this observatory, you see only the satellites that are painted in blue above the horizon. All the others are below the horizon. We don't see them. The fraction of how many you see depends on the altitude of the satellites, and here you have the function, the thick line. So for satellites at 500 kilometers, we have a few %, and satellites at 1,000 kilometers, we're at about 10%. It's interesting to note that if you look straight up, you go through the thinnest part of the constellation, while if you go close to the horizon, you cross a much thicker part of the constellation. So the effect of that is if you project the satellite on the sky, most of them will appear very close to the horizon. Okay, and if you want to quantify that, it's about 9/10 of them are close to the horizon within 10 degrees, and about 1/10 of them are in the part of the sky above 30-degree elevations where we do most of our observations. So in numbers, that means that today we would have about 100 satellites above the horizon. But if we go to many tens of thousands of satellites in the future, that number will be of the order of 5,000. above 30-degree elevations, about 0.5% of the total population. That means about 10 today and 500 in the future. So that's for the number above the horizon. But to be observable, the satellites must be illuminated by the sun. The satellites have no, thanks Lord, the satellites don't have headlights. So to be able to see a satellite, the observer must be in darkness. And so here I take again the observatory on the Earth with the local horizon, and we are in darkness because the sun is below the horizon. And the satellite above the horizon must be illuminated by the sun. So in this case, these two satellites would be illuminated and visible from my observatory. Of course, this depends on the altitude of the satellite and the elevation of the sun below the horizon. So if we go 1 hour later, some of the satellites will be in darkness, while the highest one will be still illuminated. So important note, higher satellites remain illuminated longer. So if I run the simulations overnight, this is the kind of things that you will get. So this is a map of the sky with the horizon all around, the zenith just above me, and the color gives you the density of satellites. So here it's in satellite per square degrees. And this is for a simulation with 64,000 satellites. You see the curtain opening and closing, the black curtain, that's the shadow of the Earth going through the different shells of satellites. And you see that some of these curtains open faster and some other closer. That reflects the altitude of the constellation. These funny drapings that extend east-west, that is the edges of the constellations where you have an overdensity of satellite. This is for 40 degrees latitude, but it's fairly representative of what you have anywhere on Earth. Okay, another way to look at it is a map of the Earth. And here you see the Earth, and the little dots mark the position of the Starlink Generation 2 satellites on a given time. The thick dots, the big dots here, are those that are visible from an observatory in London or from an observatory at the VLT in Chile. The yellow ones are illuminated, the black ones are in darkness. So that means you see here we are in the night, close to the terminator. So that means that we are in night but in twilight. And we have a bunch of satellites that are illuminated above us, but the other half is in darkness. That's the curtain effect that you saw on the previous slide. Here in London, we are close to midnight in summer, so we are close to the terminator again. So, you know, guys, you don't have night in London in the summer. You don't have astronomical night. The sun does not go low enough. And so that means that there are still some satellites that are illuminated. Okay. To summarize, this is a busy plot, but let's go through it because it shows some interesting things. In X, it's the sun elevation below the horizon. So 0 means sunset or sunrise. Here on the left, the dark blue one is when the sky is blue, it's daytime. And in twilight, we move to darker and darker sky to eventually reach the full astronomical night. And as the sun goes down, we reach midnight, which is the limit of the night. As the sun has a different declination, the duration of the night is different. It's shorter in summer, it's longer at the equinox, it's even longer in winter. In Y, I have the number of satellites that are illuminated above the horizon. Careful, it's a log scale, so this is 10, 100, 1000. The thick line is the total number of illuminated satellites, and you see that we start at several hundred, almost 1000. it goes down as the satellite falls in the shadow of the Earth and eventually reach zero. So first note is that in summer, you still have satellites in the sky illuminated at midnight. In winter, no, but in summer, yes. So the colored lines correspond to the different constellations, and here it's really interesting to see that a high altitude constellation like OneWeb at 1,200 kilometers or Samsung at 2,000 kilometers remain illuminated much longer during the night, and you see that the Samsung and the OneWeb dominate completely the total after a few hours in the night. The Starlink satellites, even though they are much more numerous, we're talking, this line is 30,000 satellites versus 6,000 for the OneWeb. So 30,000 satellites, but because of the low altitude, they drop in the shadow much faster than the high altitude satellites. So what does it mean for a given observatory? This is for Paranal, and this is the number of satellites as a function of time, and this time is the clock time, so midnight is in the middle. You see that the number of satellites above the horizon is constant. What changes is the number of satellites that are illuminated. They drop as the satellites fall into the shadow. They reach close to zero at midnight, and then the other way around in the morning. This is above the horizon. We start at about 2,000 satellites in this simulation, and above 30 degrees, about 10 times less, so 200 satellites going down very quickly and reaching zero something like 3 hours after sunset. The effect of seasons, here I split summer on the left, winter on the right. You see that the nights are much longer in winter, so the sun goes down much more below the horizon and we reach zero satellite, while in the summer we still have some satellites at midnight. The effect of latitude is quite strong. So if you look at the left plot, X is time of the clock, so 6 p.m. until midnight, and Y is the latitude. So London would be about here at 50 degrees. The color, again, gives you the number of satellites illuminated above 30 degrees for the left, above horizon for the right. And so if you take a place at the horizon, you see that at sunset, the number goes down. At twilight, it drops precipitously and reaches zero. In winter, you get much more dark night in terms of satellite, but in summer, you still get some satellite during the whole night. And London would be about here. It never reaches really twilight, and the number of satellites remains pretty high. Okay, so all that is to give you a feel of the number of satellites. The next question is, how bright are these satellites? And the various parameters come into play. First, size and distance. You know, it's a small versus far away question. Same. So a small satellite can be very close. A big satellite can be far away. So you really have to take both into consideration. The other element is the albedo, or the reflectivity. So a satellite painted in white, which would be stupid, but a satellite painted in white will appear much brighter than a satellite painted in black. And finally, there are also the effect of flat reflective panels that would act as a mirror and cause flares. For this talk, I'm not going to talk about that because it's really complex. It's a really complex problem. So there has been a talk yesterday about how this can be tackled. We are not there yet for our simulations. So there are many observations that are becoming available, and this is several hundreds of measurements of satellite brightness that have been performed at the Pomenis Observatory. And if you look at the orange, which are the VISOR-SAT Starlinks, and the green OneWeb, there is a clear trend. Just to fix the idea, this is the limit of what is visible by naked eye. Everything above the line is visible, everything below is too faint. The line is thick because there is no clear limit. So the top of the line, magnitude 5, I would say that's a normal person from good sight. And magnitude 7, that's a young person with very good eyesight from a superb sight like Paranal. So everything above would be visible, everything below too faint. So my job is to try to model that, and so we have a super simple function that reproduces it. You see that at this stage there is still quite a dispersion, but for the purpose of this simulation that is sufficient. So if we now put everything together, and this is a night over Paranal, you have here the bottom left the night sky with the satellite zooming by, and you see most of the satellites are close to the horizon. You have a top view and a side view, looking in one direction, looking in the other direction. And there you see the sunshine going through the satellite, and then the shadow eating them one after the other. The plot on the right is a histogram of the satellite, the number of satellites as a function of elevation. And again, most of them are bunched close to the horizon. The dots show the brightness, the magnitude of the satellites. And thank you. These boxes are the region where the satellite would be visible by naked eye. Again, too close to the horizon, you don't see them because of the extinction and the obstruction. And so basically, these are the satellites that would be visible. Careful, when you see this huge burst of satellites here, it's basically daytime, so it's not really relevant. The blue box is the satellites that are annoying for astronomical observations. So we go much deeper than naked eye. That will be the topic of my second talk later. So, focusing a little bit more on the naked eye issue, let me show again the plot of the number of satellites as a function of time of night, and I zoom here on the right to the bottom part of the two plots. So it's just a change of scale. The yellow line and the red lines are the satellites brighter than magnitude 6 and magnitude 5. So magnitude 6 is something that you would be able to see in dark night, but during the twilight, they won't be visible anymore. So there is the second curve of magnitude 5 that is a little bit easier to see during twilight, but here the sky is really too bright, you don't see them anymore. And so you see that during twilight, we would see from Tololo, when there are 48,000 satellites in the sky, of the order of 40 satellites above 30 degrees of elevation. To give an idea, if you look at a site like Heavens Above, which lists the number of satellites visible today, before the beginning of the Starlink era, that number was about 5. Nowadays, it's about 5 to 10 during twilight. So if we multiply the number of satellites, this is going to go up to a few tens. The other thing is that it drops precipitously after twilight because the brightest satellites tend to fall in the shadow very quickly. So, take-home summary. all the blue numbers here refer to about 50,000 satellites, which is what we could expect in 10 years. You can scale that number. If you prefer to work with 100,000, just double all the blue numbers. So that means we would have about 5% above the horizon, so 2,500. So of these, about 1/10, so 0.5% or 250 would be in the part of sky where most observations are performed. To be visible, a satellite must be illuminated, which means that the sun must be not too far below the horizon, which means that it is essentially the beginning and the end of night, with two caveats. The first one is that higher altitude satellites will have more satellite visible for much longer. And second is the effect of season and latitude. The satellites are visible longer in summer because the sun does not go as low. The brightness of a satellite is a complex problem, so I did some simplifications and we need more data. But the result is that with the current mitigation introduced by Starlink, most of the satellites are in the 5 to 10 magnitude range, with a peak around magnitude 8. In terms of satellites that are bright enough to be visible with the naked eye, we can expect up to 50. And to give a reference, that's about 1% of the number of stars that you see in the sky. It's 4,000 in the northern hemisphere, 5,000 in the southern hemisphere. And we will be able to see that when the sun is between -12 and -20 degrees below the horizon, so the twilight. The good news is that most of these 50, will be on the faint end of the distribution between magnitude 5 and 6, with about 10 brighter than magnitude 5. So another way to look at this, here I focus only on the geometry. In a second talk later, I'll talk about the impact on observations. And if you are interested in the broader impact, I really highly recommend this paper that Andy Lawrence presented yesterday, a paper in Nature, which brushes a very broad picture of all the impacts. So this is the last slide that I leave as the end, which is really a good summary of the situation. You see all the satellites, you see those that are illuminated, those that are in darkness and therefore invisible, and that for a given observatory, the annoying part is when you are close to the terminator during twilight, and as you move deeper in the night, all the satellites fall in darkness, with the twist that if you are in summer, you might have the situation where you have satellites still visible during the whole night. When I say visible, that means detectable. In terms of naked eye visibility, you really have a very thin region where the sky is bright, the sky is dark enough, and the satellites are bright enough to be seen. And that ends this talk. Thank you.
Thank you very much, Olivier. I'm sure that that's really starts the day off well. We have a few minutes, I think, in hand, so maybe we could handle one of the questions from Doug Edworthy. Martin?
Yes, indeed. Yeah, Doug wrote, while the satellites aren't always visible, presumably they also occult very small targets as they pass between them and the observing telescope. So visible or not, they still pose a problem to observational astronomy.
I addressed that specifically in my second talk. So short answer is this is absolutely right, but this is totally negligible. And I'll have a slide in 1 hour going into more details on why it is negligible.
Splendid.
Okay.
Thank you.
Thank you very much. So thank you, Olivier, and we'll look forward to hearing your talk later on. So we have a quick question, I think, from Stuart Eves. Stuart?
Can I thank you, Olivier, for an excellent presentation? The question is, have you looked at all at the potential illumination of satellites by the moon? I believe that the magnitude difference between the sun and the moon is around 14, which, based on the numbers that you've given for satellites, would put the potential illumination somewhere in the low 20s magnitude, I think, which perhaps isn't a problem for many instruments, but for some of the very high-end ones that are being developed, they would potentially still be able to see satellites in moonlight.
Okay, you are right. However, it's even worse than the difference of magnitude, because you have to take into account the position of the moon. And if the moon is bright, it's above the satellite, which means that you see the dark side of the satellite, and so they are even much fainter. We're talking about magnitude 30 or so. Also, if you take the half moon, basically, when the effect is worse, then that would bring the satellite to magnitude 28 or so. So it is also completely negligible. Something that we considered also is the Earth shine on the satellites, and the effect is also completely negligible. So really, what is important is the sunlight reflected. Makes sense. The sun is so bright that illuminating the satellite with something else will be much fainter. So it's really the sunlight. There has been at some point some discussion to equip the satellite with some illumination, some LEDs, to make them easier to spot. Of course, that would be a terrible idea.
Yes, I actually deleted a slide showing the Japanese satellite that trialed a system from my presentation yesterday, but I share your view that that's not a great idea. It was actually the half moon scenario that you described just now that I was wondering about, but it's quite reassuring to hear from you that you believe that that's a negligible effect. So thank you very much.
I don't have that slide in this deck, but if you look at the geometry and then run the numbers, it's actually very quickly very clear that it's not a problem.
Does that take into account the fact that the orientation of the satellites will be to minimize reflections down to Earth from the sun, and the orientation of the satellite may not be optimal to prevent reflections, glinting reflections from moonlight?
You can have a glint reflection. The good news is that even if you have a perfect mirror, the reflection from the moon will not be very bright, first, because the satellites are small, and second, the flash will be very short. Yeah. I don't have... Yes, I do.
I think maybe some of this will be covered
we can take it in the discussion.
And or later on in the discussion later on. Yes. Okay. Thank you, Olivier, and thank you for your question, Stuart. So, Harry, if you're ready to go.
I am here. So let's see if I can share my slides here. Okay. Are you seeing those okay?
Yes, thank you. Yes.
Excellent. All right. So my name is Harry Krantz. I am a PhD student at the University of Arizona Stewart Observatory. I'm here to talk about what I've been doing for my thesis work. Also want to represent my advisor, Eric Pierce, who has spent most of his whole career studying satellites, doing photometric characterization of satellites in the SSA industry, and my other colleague, Adam Block, who some of you may recognize the name from his astrophotography. So we're going to be talking about the Plomanus Leo satellite Mega-Constellation survey. So we've been observing these satellites, the Starlink and OneWeb satellites, for the last couple of years. Once this kind of came to the forefront of things that are people interested in. And I'll just get into it then. Let's see. There we go. So first question is, why do we even want to observe these satellites? And this was something that came up at SatCon 1 almost 2 years ago now. And really, it comes down to the question that people are asking is, well, how bright are these darn satellites going to be in my images? Because no matter what we do, these satellites are always going to be visible in images. We might be able to get them dim enough where they're not visible to the naked eye, but they're always going to show up in your images if you're using any kind of telescope, even a small one. So we really want to answer the question is, well, how bright are they going to be? And we want to quantify that in a way that's relevant to astronomers. And this is a hard thing to do, since not all telescopes are the same. You have small telescopes, big field telescopes, small field telescopes, different kinds of cameras, and so on. So what we're trying to do is just make a quantification of the brightness in a way that astronomers and other people who are interested can take that information and figure out for themselves how these satellites are actually going to impact their science or their observations. We also want to note that satellite brightness is very dynamic and hard to model accurately. And I like to emphasize this at every talk I give, is that one number really does not capture the full situation. We see a lot of things, particularly the recommendation that the satellites should be less than 7th magnitude. And you really can't describe satellite brightness like that. It's much more complicated. So we really need to do, and what we're trying to do with our survey is to measure the apparent brightness in all geometries across the entire sky. Lastly, what we want to do is we want to test if mitigation attempts are really effective. It's easy for SpaceX or whomever to come out and say, oh, we've changed something about our satellites, either the flight configuration or adding the visors or doing the dark sat modifications, and say it's working, but we really don't know if it's working until we have the numbers on paper. So this is Pomenis, and I like to emphasize this is a small telescope system that we purpose-built for observing satellites about 5 years ago. It was before we even knew Starlink was a thing. Like I said, my advisor's been in this industry for a long time, and this is one of his kind of dream systems that he always wanted to build, is this small aperture but extremely large field of view. So it's about 4 degrees square that we can see. All in one image. So even though it's a small aperture, we can see a lot of the sky, which makes it very useful for looking for satellites, especially things we don't have accurate orbital elements for if we're trying to find a lost satellite or something like that. Otherwise, any of you astrophotographers out there might recognize some of this equipment. It's a Takahashi Epsilon astrograph. We have an apogee camera, 7-color filter wheel on a paramount. And then also I like to emphasize this is in a mobile enclosure. This was my own design and creation. It's my first project as a graduate student, was to design the enclosure for this thing, which is on a trailer, so we can actually pick it up and take it anywhere we want in the country. Like for satellites, you can't see them from everywhere around the world. You might have to be in a specific spot to see a specific satellite. So we have this mobile system that we can take wherever we need to do the science we need to. So in brief, how do we observe LEO satellites? They move quite quickly, on the order of a degree per second. Very difficult to track. We can actually track them with Pomenis with a bit of effort. However, for our survey, we selected to do a different method that's much more reliable and less time consuming than trying to track each individual satellite. So in brief, we essentially slew to the expected RA and deck position, which we calculate from the satellite TLE. We record a clean image of the sky and background stars, which is shown in the upper right there. And we continue to track this position at a sidereal rate. We tracked it for about 60 seconds or so. Then we trigger the camera at the time of the satellite crossing. So this is one of the more difficult things to do with most astronomy and equipment, because most astronomy equipment is not made for precise timing of events, because usually stars and things are where you left them. They don't move around on the sky. We figured out a way to use our system to do this precise timing and able to capture the satellite streak as it's crossing the field of view and capture it entirely in the field of view. So we see the whole streak there. It's not going across the whole frame. And again, this is where the large field of view really comes in handy, that 4 degrees. So even with a short couple of second exposure, we capture the entirety of the satellite streak, which makes it much easier to do the photometry. So this is how our data processing works. Again, in a very brief explanation, We don't have time today to go through the entire complicated process, but it's essentially a semi-automated pipeline that processes the images, does standard dark flat bias corrections, and then selects and extracts the satellite streak, which you can kind of see the selection map here. So all the background stars, and then you have the big satellite streak highlighted in green. And then measures the photometry, does all the corrections, yada, yada, yada. And at the end of the day, what we have is a SQL database where we compile all this information. So we have things like measured flux and the calibrated apparent magnitude, which we just made from all our observations. But we couple this with also making a true astrometric position based on the streak in the image. We essentially take the centroid of the streak and call that the actual position of the satellite on sky at the time of observation. We can compare this to the expected position on the TLE. I don't have a slide on that today, but I can tell you very briefly that the accuracy of these ephemerises from the TLEs are actually quite good, on the order of 1 to 3 arc minutes. Typically on the lower side towards 1 arc minute. Of course, the distribution has a large tail that extends out to 1 or 2 degrees. But when you get out to that point, usually what you're dealing with is a stale TLE or a satellite that's made a maneuver since the most recent TLE. And we've been working with Dr. Kelso at Celesttract and SpaceX to understand exactly what their ephemeris information is that they are sharing with Celesttract that has that future predictions involved. So we're also coupling these observations in our database with other things like orbital parameters. So you have phase angle, range, etc. We also have satellite models and submodels. So we have like Starlink OneWeb, but you have also the various versions of Starlink satellites. And then of course we maintain, archive all the TLEs that have been issued for each satellite. So we can make assessments in the past based on our observations. We don't need to go and figure out where the satellite was. We just have the TLE from the time. So in summary, our photometric survey, our goal here is to build a statistical model. So this is taking empirical data and using that to essentially say, what does the whole picture look like? We've been doing this almost nightly, pretty much as long as there's a clear sky overhead, and we have very loose requirements for a clear sky. Half our measurements sometimes are going through thin cloud cover, but at the end of the day, it really doesn't matter for us. And this data I'm sharing today is up through December of last year. We are continuing to take data today. However, today I'm just sharing data up through December, where we still have to process the data from the last few months. In total, we have over 12,000 separate measurements. I want to emphasize that these are separate measurements, different from what you've seen from other people, where they take a short track of one satellite and extract 100 measurements from it. This is 12,000 separate individual satellite measurements taken at different times at different orientations in the sky. And this covers almost 1,800 individual satellites. I believe the number today is we have maybe 2,500 of these Mega-Constellation satellites in the sky. So we're looking at a good fraction of them we've seen before. And of course, since the survey is ongoing, eventually we will hit all the other ones as well. A majority of these measurements have been made from the Mount Lemmon Sky Center, which is just north of Tucson, Arizona. We did take some measurements from other locations. Like I said, our system and enclosure is mobile. So it was actually in 2020, there was a wildfire, a forest fire up on Mount Lemmon, which forced evacuation of the Summit Observatory. And luckily, nothing was harmed in the fire. But when the fire was coming up the mountainside, we said, hey, our telescope's mobile. Let's just pick it up and get out of here. And we moved it down to a different location and continued doing observing while the wildfire passed over the mountaintop. So this is what the photometric results look like. So I'll explain here what we're seeing. Essentially, this is looking at the sky from the bottom, zenith in the center. Your cardinal directions. Each dot here represents a satellite we observed at the location in the sky we observed it, and the color corresponds to the visual magnitude. You can see the scale on the right, where red and darker is a dimmer satellite, and then like a black body spectrum, you go up through the colors through orange, white, and then white as a brighter satellite. You can also see these big swaths of yellow just below the horizon on the east and west. And so this is also plotting the position of the sun at the time of observation. And you can see it's all smeared across because, of course, we're looking at the sun over a year. Over the seasons, the sun will move its azimuth across the sky. And so you see here is kind of a mess of all the points plot on top of each other. And because of the sun's position, nothing really correlates. So what we can do is we can exploit the fact that the sky is symmetric around the zenith. And so we can rotate each measurement around zenith and place it on the sky such that the sun azimuth for every measurement is the same. And now we can see a pattern. I'll talk a little bit about the fact that we can't do the same in elevation angle because the sky is not symmetric in elevation angle. However, even though the sun technically is moving further below the horizon by 10 to 20 degrees over the course of the couple hours of twilight during our measurements on each night, this actually doesn't change the pattern when I've looked at it. I don't have a visualization for it today. But the pattern itself does not change. So we're not very concerned about trying to correct for any elevation angle or change in the position of sun as it moves further below the horizon. So here are some comparisons of the different satellite models. So on the left, we have the standard Starlink models, the first generation ones, which people noted for their brightness and surprised everyone off guard when they first started appearing in the sky. And on the right, we have the visored Starlink model. So this is essentially the same exact satellite, except it has the addition of those two sun visors that hang below the satellite chassis. You can see it in the diagram there on the lower right. Excuse me. And you can see that the addition of visors did make a drastic difference in the brightness. However, it didn't eliminate all factors of apparent brightness. So on the left here in this plot of the standard Starlink, you can see we have very bright satellites around zenith and then towards the sun. We also have very bright satellites opposite the sun and these kind of flanks on left and right of the sun that are a little bit dimmer. You see kind of a same pattern on the visored satellites. However, you see the biggest benefit from the visors come from the flanks towards zenith. However, opposite the sun, you have almost no change in apparent brightness. I will emphasize, though, that these are just kind of a one moment in time snapshot of what the sky would look like if you saw a given satellite there. Of course, as the evening goes on, you have the Earth's terminator, the Earth's shadow, climb up across the sky opposite the sun. So these brightest satellites are going to disappear first into the Earth's shadow, whereas the satellites near the sun are going to disappear last. And then, of course, we have OneWeb. So we have all three on screen now. OneWeb, we don't have as much data for, and it's a little bit biased in its sampling. So you don't have quite as much sky coverage as we do with the Starlink satellites. But it is very apparent off the bat that the OneWeb satellites are much dimmer, usually in the 8th, 9th, or even 10th magnitude range versus the Starlink satellites, which are more like 5th and 6th magnitude. You also don't see as much of a pattern in brightness with the OneWeb satellites, and that's because they have this more boxy shape, which produces less specular reflections than the Starlink satellites and their flat panels. However, you do see an increase in brightness closer to zenith and then just slightly opposite zenith from the sun, where you're getting some more back reflection. So back to our original question is, well, how bright are the satellites going to be in my images? And in order to kind of answer this question, again, magnitude is not really the best way to do it, because you can tell someone a magnitude, but that's an instantaneous magnitude of the satellite. It doesn't really correspond directly to how bright it's going to be in the image without doing a fair bit of math and other work to think about it. So what I've done here is I took the apparent magnitude and you calculate the expected photon flux for an imaginary telescope with a 1 meter aperture. Of course, there are many other factors here, but I tried to make it essentially a unit telescope without putting too many complications in, like the sensor sensitivity or other factors. It's also key here to understand that these satellites are moving. So when you take an image of the sky, excuse me, and you see a satellite streak in it, that satellite streak essentially has a finite brightness. It doesn't matter if you take a 10-second image or a 100-second image, because that satellite's moving, it moves across each pixel in your image at the same rate. And that's essentially setting the effective image exposure time for that satellite on your imager. So really what we're looking at is, well, what is the expected number of photons per arc second of satellite streak? So you can think of this as if you had 1 arc second size pixels, which is not uncommon to have for an imager. This is how many photons you'd expect per pixel in your imager. And you can start to make determinations of, well, if it's this many photons, then I'm either going to saturate my detector, which is bad, or it might be 50% of my photon or limit, or my counting limit in the detector, or it might only be 10%. This can give you an evaluation of, well, how easy is it going to be to subtract this streak out of the image, and how is it going to affect your science target if it were to overlap with your science target? So this is what those same plots, that same data looks like when we convert the apparent magnitude now to a expected photon count. They don't look too different. However, it's important here to now look at the values. So we look on the left here at the standard Starlink satellites and their expected photon count. You see a lot of them are in this 10 to 4 to 10 to 5 range, and some of them are even above 10 to 5. So again, if you're thinking of a 16-bit imager, you have about 60,000 available counts before you saturate your detector. You can see that most of these are not going to saturate, but the brightest ones likely are. And of course, it depends on where you're looking in the sky. But for the standard Starlink satellites, it's almost uniform across the sky with a little bit of variation close to the sun and then opposite the sun, and of course, these darker flanks. Though it's also, remember, this is for an imaginary 1-meter telescope. Which is large in terms of amateur speak, but if you're a professional observatory working with a 6-meter telescope, you need to multiply all these numbers by a factor of 100 or so. And then it's easy to see that almost every one of these satellites is going to saturate your detector. On the visored satellites, you see a stark difference, and the pattern that we saw in the previous slide is even more pronounced now. You still have this kind of brighter spot near the sun below the horizon, and opposite the sun, they are still quite bright, almost as bright as the standard Starlink satellites with these almost 10 to the 5 photon count. Again, likely to saturate the detector even in a small 1-meter telescope. However, the rest of the sky close to zenith and in the flanks is much dimmer, kind of below that 10 to the 4 threshold. So it's not as likely to saturate in a 1-meter telescope. Of course, if you go up to a 6-meter telescope, even these are going to be threatening to saturate your detector. And then again, we have the OneWeb satellites as a comparison for all three. Again, these OneWeb satellites don't really show a distinct pattern, though you do see now that there's slightly more brighter ones near the sun, so they're starting to follow the same pattern as the Starlink satellites. And again, most of these are below the 10 to the 4 threshold, so again, not likely to saturate a detector except in a larger telescope. So, understanding satellite brightness. It's really all about the reflection geometry, and this is something I like to think about and explain to people in different ways. So it really comes down to this reflection geometry. So we have all these angles, particularly the sun satellite observer angle. So what angle are you looking at the satellite, and where is the sun relative to you? You can draw a triangle. You also have to consider the range. Well, how far away is the satellite? And this is, of course, because of the inverse square law. So for diffuse reflections, the light will tend to be dimmer the further away you are. With specular reflections, it doesn't drop down as much. So if you're looking specularly, it almost doesn't even matter how far away the satellite is. It's almost going to look exactly the same if you're 100 kilometers or 1,000 kilometers away. Position in sky, of course, is related to all this geometry we just saw in those sky plots. Where you're looking in the sky, where you see the satellite matters. And satellite attitude and pose also is a very important factor. Luckily for the Starlink and OneWeb satellites, we can assume that the pose of the satellite's almost always going to be the same because these are active satellites and they want to orientate their solar panels antenna to do their job as they're intended to do. This is different than a lot of my research, which has to do with old dead satellites and rocket bodies where we don't know the pose or the pose is constantly changing. And then, of course, satellite size, shape, and materials determines, well, how much light is it reflecting, how is it reflecting it, what color band, et cetera. And the last thing to understand here is the difference between diffuse and specular reflections. And I'll talk a little bit more about this in another slide, but you can kind of see on the cartoon diagram here that things like solar panels, big flat panels, shiny things will create specular reflections, whereas other things will create more diffuse reflections. And so when we're looking at the satellite, really we're seeing a mix of all these discrete reflections of all these components and adding them all up into a specific orientation, and that's what determines the overall brightness. So here's a cartoon diagram that I'm sure many of us have seen before of how a satellite goes around the Earth and sunlight reflects off of it, and you have your observer down there on the ground. Though I'm going to emphasize today to erase this from your mind. It's not very helpful to understand exactly what's going on here because things are really not to scale. So instead, think about the Earth as being a flat plane. It's a flat Earth in this world. When we're talking about LEO satellites, they're so close to the surface of the Earth relative to their orbit that we really can kind of think about them in this way. There are slight curvatures and angles at play, but for our analysis, it's better just to think about this as a flat Earth with a satellite flying over horizontally and your observer down here on the ground. So as the satellite moves across the sky, we have essentially 3 different domains we see in terms of reflection. Overhead, we're getting largely diffuse reflection. That's what we're seeing in our brightness. However, in other orientations, so we go closer towards the sun over on the right side, we get forward specular reflections. And then on the other side, we get backward specular reflections. And again, this has to do with essentially the geometry. And it's easier to think about it this way than with a round orbit, especially with something like the Starlink satellite. So if you imagine there was a flat panel there, just a horizontal flat panel flying overhead, you can really start to think about, okay, if it's directly overhead, I'm really just seeing myself. But if it's over on the right side, well, now you're seeing this reflection of essentially the sun, which is over there off the screen on the below the horizon. And then with the Starlink satellites, you also have this solar panel that extends vertically. So now you can understand why we have these backward reflections coming off the solar panel. So modeling satellite brightness, it's really hard to do well. People have been trying to do this for over 60 years, going back to the very first satellites in the 50s and 60s. And there's been lots of attempts, and no one's really come up with a way to just do it off the bat. Common models use diffuse spheres, a Lambertian reflecting surface. And this is actually pretty good for making very approximate estimates. I use it all the time for different research projects. We say, well, how bright is the satellite going to be, especially for things far away in geo or further orbits? You can get a ballpark measurement. You can say, oh, it's going to be 7th or 8th magnitude. But it's really not good for specific measurements. It loses a lot of the fidelity and a lot of the geometry of these satellite reflections. You can look at more complicated models that use 3D models of the satellite, BRDFs, and so on. And people have been doing this, and they work quite well for very specific situations, but they are not well proven or generalizable in any kind of manner when you have things across the entire sky, or you have satellites you don't know exactly what they're made out of. That's a key important thing to do if you were going to try to use a BRDF. You have to know the exact shape and size of the satellite as well as the materials it's made out of. So I have a different model I like to use, which I came up with for this project, which I call the effective albedo model. So essentially, we're skipping all this complicated, detailed modeling of the satellite reflection, and we're going to try to jump straight to the answer. So what question are we trying to answer after all? And to me, I think the question we're trying to answer is, well, can the satellite be less bright? If we're talking to SpaceX or when we say, your darn satellites are too bright in the sky, they are ruining my stuff, can you make them dimmer? Well, the answer is, well, can we make them dimmer? The diffuse brightness is very hard to reduce. And they're almost all the same on satellites. When you measure them, you get about a 10 to 20% albedo, a bond albedo, which is kind of a full wrap up of everything that's reflecting. And very few satellites manage to get below that 10 to 20%. And even the Starlink satellites in diffuse space are about 10 to 20%. So at the end of the day, without making satellites smaller, they're not going to get any dimmer. So the real question is, well, when is it not being diffuse? And that's what this model tries to do. So we take the diffuse sphere model. We know our observed brightness. We know the real apparent brightness. So we can invert the model and instead calculate what I'm calling the effective albedo. So this is the albedo that this object would need to reflect as much light as it does if it was a diffuse sphere. So this is not a true physical albedo. However, it's really giving us a measure of the reflection specularity. It's saying, well, when is it reflecting more light than just a diffuse sphere? When is it being more specular? So if we look at the plots again, now plotting the effective albedo, we can see where the satellites are acting diffuse and where are they acting specular. And again, what really stands out here is the geometry close to the sun near the horizon. You get this very strong forward specular reflection, versus the rest of the sky, where the satellite begins to look almost uniform across the sky. You see the visored satellites are cutting down a lot of the reflection across the mid-sky. You do still see a lot of specular reflections near the sun, where the visors are actually failing to block enough light to reduce it. It's a little bit better than the standard Starlink satellites. You also see on the visored satellites opposite the sun, slight increase in brightness. And this may actually be light reflecting off the visors instead of the visors shadowing the satellite. And again, we have the OneWeb satellites for the final and comparison between all three. And now you see the OneWeb satellites also experience this forward specular reflection near the sun, not as bright as the other ones, but also still brighter than it would be if it was a perfectly diffuse sphere. So in conclusion, these are my takeaways for you. This is not a simulation, this is real data. You see a lot of plots that kind of look like this that are all based on simulations, but this is not a simulation. This is real data. This is exactly how bright they are in the sky if you were to go stand outside tonight and see them. And also satellite brightness cannot be described by one number. We just see in these plots, we can't quote a number at zenith and say this is how bright the satellite is. You really need to look across the whole sky and see the range of brightnesses that you can see. It ranges by a couple magnitudes depending on where you're looking. Satellites are not always brightest at zenith. In fact, for all of these satellites, they're not brightest at zenith. They're all brightest either opposite the sun or near the sun, nowhere near zenith. And of course, mapping the reflection patterns like I did, I think is going to be key for observers trying to avoid the worst impact. So if you have a map like this and you have a telescope and you're trying to avoid satellites until they're all in shadow, you'd say, well, let's avoid these areas of brightest satellites and let's look somewhere where the satellites are darker. And that is the end of my slide deck. So thank you very much for listening to me today.
Thank you very much, Harry. That was a fantastic talk, and you've had some very good feedback here in the chat.
Excellent. I can check.
Will you be available to be around for the Q&A later on?
Yes.
I appreciate that it's a very unsociable hour for you where you are. Good.
That is quite all right. I'm going to be observing tonight or tomorrow night anyway, so I'm switching the night schedule, so it's all good.
That's great. Thanks very much. So we'll break now for lunch. We return after lunch at 12:45 when we have the second of Olivier's talks. Thanks very much, and thank you again, Harry. We'll see you all later. Thank you. Bye. Back, everyone. Hope you had a good lunch or good breakfast, or managed to get a few more minutes sleep. Great talks this morning, and we have now the second talk from Olivier Hainaut. So over to you, Olivier.
Thank you. So hello again. So same thing, share, full screen. And incoming, yep.
Yes, we got that.
Thank you. So this is really a continuation of my first talk, and it was fantastic to have the talk on the Pomenis observation in between, because I'm already going to use them. So this time I want to quantify the effect on optical observations, basically to say how much are we going to lose in terms of imaging, spectroscopy, thermally, infrared, transit, etc., depending on the telescope, depending on the conditions. So this is the kind of effect I'm talking about. This is an image from the VLT, and a satellite crossed the field. So question is, how frequent is that, and how much are we going to lose? So the first question I want to address is how many trails are going to be present in my field of view. And here you have a hypothetical sky view with the dots marking the position of the satellite, and here a huge field of view. So how many satellites are in this field of view? It's easy. You just need to count them, and you can do that either by simulating each satellite, or using the densities that I described in the first talk. However, that's not the whole story, because the satellites are moving, so instantaneous observation is not realistic. So you have to consider long observations, where long is as short as 1 second. The satellites move so fast that you really need to take into account. So there, the number of trails that you see can be also computed as a density of trails in the sky multiplied by the size of the field of view multiplied by the exposure time. And the density of trail is something that we can compute. It's the density of the satellite multiplied by the apparent velocity of each of these satellites. And so we also produce this kind of maps showing the density of trails. If you combine, then the number of satellites and trails in your field of view is just the sum of the two. And it's this nice simple equation. So number of satellite is the area of the field of view multiplied by the density of satellite plus the size of the field of view times the exposure times the density of trails. We validated that equation using discrete simulations, and it works really well. The next step is to take into account the effect of the magnitude of the objects, of the satellites. And in what I'm present, I use the simple approximation of a line giving the magnitude as a function of the range of the satellite. And I'm really looking forward to contact Harrison Krantz to see how we could integrate their results into our simulations. The alternative would be to use the full bidirectional reflection diffusion function for more detailed simulation, but as Harrison has explained, this is horribly complicated. So I think that the solution that he presented in previous talk is really the way to go. Another issue is that the satellites appear defocused and resolved from our telescope. The reason is simple. They are so close that we see them not as a line, but as a trail. This is kind of an extreme result, but you see that the satellite is really completely resolved. In the following simulation, I neglect that, which means that my simulations are conservative because I consider that the satellites are brighter than they really are. The other element that we need to take into account is the angular motion of the satellites. The satellites move, so they do not appear as a point source, but as a trail, and that reduces their effective brightness. Basically, it does not matter how long your exposure time is, the time that the satellite is going to stay in a pixel is always the same, and that depends only on the velocity of the satellite. So there is an equation to compute it, but the result is shown in this plot here on the left. The red line is the magnitude, the integrated magnitude of the satellite as a function of its altitude. And you see that a satellite at 500 kilometers would be of magnitude 7 or so. As shown before, this is simplified, but it's good enough for what I'm going to do now. If you take into account the exposure time that you're dealing with, let's say a 60-second exposure, the effective magnitude is much lower. So that means that a satellite of magnitude 7 will appear as bright as a star of magnitude 17 or so. And so that is actually quite important, an effect that you must take into account. Something that is completely unintuitive then is that the limiting magnitude for the satellites almost does not change with the exposure time of your exposure. Here, this is the limiting magnitude for, I took an astrophotographic camera, but you could do that the same for a telescope. The red line gives the limiting magnitude for stars in the field, and so for a 15-second exposure, you would go to magnitude 10. Then it goes slowly down as you gain more signal from the stars, and as the sky background becomes more and more important. So it's the fight between the signal from the star and the noise from the sky. For the satellites, however, you see that it's almost constant. If your limiting magnitude is 10 for a star, you will see satellites that are about magnitude 4 and brighter. The other ones will be too faint to be detected. So if we combine all that, I know now how many satellite trails I will have in the field of view. I know how bright they are, and I can also estimate how much data I'm going to lose. So in this example, what I say is that, okay, this trail, it might be possible to subtract it, but I don't trust subtraction. Usually it will always leave some residual. So what I do is I mask it. So I say that this trail is basically lost data over 10 arcseconds wide. And so that allows me to compute how much data I'm going to lose. And so this would be a map for this instrument, for FORCE, of the fraction of the pixels that I'm going to lose. And if I look at zenith, you see that the color indicates dark green. So we are about here at 0.5% of the data being lost. Closer to the horizon, it's much higher. If you go into the shadow of the Earth, then it drops to 0 because the satellites are not visible anymore. And of course, this is just for one instant in time. I have to evaluate that over the night. And this is something that we have done for various telescopes. So here, basically, this plot on the top would be the same, so somewhere here in between. And we can go from twilight all the way to dark night and quantify the average loss in the sky. And you see these are the small percentages that I listed here as a function of the solar elevation. And we are talking typically of the order of a little bit less than 1% at twilight and much less later. Just to remind you, this is really just an effect of the satellites, the illuminated satellites falling into the shadow of the Earth. And so as the number of satellite illuminated drops down, the effect on the observation decreases. The difference now is that we quantified that effect. So we can run that kind of simulation for various instruments. And here I just present 4. So FORCE on the VLT, my favorite instrument, and at twilight with 64,000 satellites, so 2030 or so, we would lose 0.4% at twilight. Other telescopes, it really depends. You have to take into account typical exposure time, you have to take into account the field of view, the size of the detector, but at the end, this wide field camera would lose 0.2%. This is a super wide field camera on a smaller telescope, and there they would lose only 0.03%. What saves them is that the smaller telescopes makes that the trails will be less annoying. Okay, here at the bottom right, you have the case of the LSST, the Vera Rubin Observatory, which is a large telescope, 8 meter, with a 3-degree field of view, average exposures. And you see that the situation here is quite bad. We are talking about tens of percent. The average over the observable sky is 22%. So let me go a little bit deeper in that case. They suffer from various problems. First, it's a huge camera, so they will see more satellites. Second, it's a large telescope. It's 8 meter, so the satellite will appear really bright. Then their camera suffers from saturation. So that means that if the trail of a satellite reaches magnitude 7, again, you have to take into account the velocity, but it's a good it's a good benchmark. See, if the satellite is brighter than magnitude 7, the detector will saturate, and that basically ruins not only one trail, but it can ruin a whole CCD of their mosaic. And then the electronics suffer from crosstalk. You see here an example. The satellite trail is the bright line at the center, but you see that there are some ghosts going parallel on each side, and that is crosstalk in the electronics. It can be partially mitigated, but of course, correcting data is always problematic. And so if you combine all that, the losses for the LSST camera will be much higher than for other imagers. There are also different science cases. And here, let me see if that works. Yeah, it's working. If you want to observe comets, comets tend to be visible quite low on the sky, and you have to observe at twilight. And from all what I've said below, low on the sky is worse because there are more satellites. In twilight is worse because there are more satellites illuminated. So this is basically the combination of worst factor. This is a very fresh video from my friend Alain Maury, who has an observatory at San Pedro de Atacama. If you don't know about it, go and check his website. It's Space, San Pedro Space Exploration. Celestial Exploration, I missed. So you see this video covers about 1 hour, and on average you get of the order of 0.5 trail per exposure. So every second exposure has 1 trail on average. This is today, well, yesterday. If you go to 60,000 satellites, it's going to be obviously much worse, and he can expect of the order of 5 trail per exposures. And again, in this case, the mitigation is complicated because if you want to observe that comet, you have to observe in the worst place of the sky at the worst time. Now, let me change instrument. There is the case of spectrographs, and of all the observations done behind me at the VLT, over half the observations are in spectroscopy. And the goal is you take part of the light from the sky and you disperse it with a spectrograph, which is a glorified prism to spread the different wavelengths, either in a line like here or in a series of orders, and on this high resolution spectrograph where the spectrum is basically taking each line and putting them at the end of each other to reconstitute a huge spectrum. And this is what the spectrums look like. And the problem is that if a satellite crosses the slit of the spectrograph, you will get an additional spectrum. And the situation is that if the satellite is much brighter than your science object, so if the orange line is 10 times brighter, you will see it immediately. So it's clear that you have an obvious loss. Similarly, if the satellite is much fainter than the science object, if it's 10 times or 100 times fainter, you don't really care. The problem is that, as in this example, if they are about as bright as each other, when you look at the spectrum at the telescope, it will look normal. But it's only when you will look at the data, that you will analyze the data, that you will get something really weird. If your science object is a quasar, and the satellite is essentially a solar spectrum, solar light, you will notice that there is something weird, and you will say, oh, it must be a satellite. If your science object is a star, and you put the spectrum of another star in top of it, then you will end up in the situation where, okay, what's going on? Is my star misbehaving, or did something happen? So this is the weird situation of spectrographs. You don't have trail, and you don't necessarily immediately realize that there is a contamination. So in terms of the effective magnitudes of the satellites, if you take again my reference satellite magnitude 7 at 500 kilometer and see how it goes for exposures of 300 to 2000 seconds, you get these magnitude of between magnitude 20 to 23. The boxes give you the sensitivity of our spectrographs on a large telescope. Good news is that the high-resolution spectrographs are not sensitive enough, even on an 8-meter telescope. But the medium or low-resolution spectrograph will be exactly in the range of magnitude where you can get blind contaminations. So this is something that we have really to consider. The type of saturation, again, in the case of a high-resolution spectrograph, completely black, nothing is detected, 0% loss, that's fine. For medium-resolution spectrograph, we can get at twilight up to 8–9% of losses. So this starts to be significant. There is the weird case of multiplexed spectrographs. So the idea is that you put many, like 2,000 optical fibers in the focal plane of the telescope and route all these fibers to your spectrographs. And there we ran some simulations to see how much the satellites would affect. And typically, if you send the satellite at random through the field of the fibers, it will hit 1.3 fibers. And so we get, therefore, that the losses for this instrument will be of the order of 1% at twilight in low resolution. And in mid-resolution, because the spectrograph is less sensitive, it drops by an order of magnitude. So just one parenthesis is the case of thermal infrared. If we observe in the thermal infrared, so wavelengths of 5 to 20 microns, the satellites are actually bright. They emit radiation just because they are at about 300 Kelvin or 20 degrees centigrade. Okay, we ran some calculation to try to see the type of flux that we would get, and we end up in fluxes that are actually quite bright. They are easily detectable. And again, this is the intrinsic emission of the satellite. So even when they are in the shadow, they don't cool down instantly. So they will continue to emit during the whole night. What saves us in the case of thermal infrared is that the exposure time tends to be extremely short. The field of view is small, and so the probability to have a crossing is very small, 1 in a million. Furthermore, with these fluxes, you can get a signal to noise of 10 to 50, which means it's very, very easily detectable. The good thing is that you don't take only one of these images, you take typically hundreds or even thousands of them. And so once you combine all the data, you end up with a satellite that is below the detection threshold. So not only they are actually faint enough, but the probability that a crossing occurs is very small. So it's not an issue. Satellites are not an issue for thermal infrared. In my previous talk, someone asked about the satellite passing in front of a star. And yeah, that will happen. And we can evaluate from the motion the duration of that eclipse, and it is of the order of 1 millisecond, just because they are moving really fast. And we can also evaluate the probability for that to happen, and it's 10 to the -4, so 0.01% per star per 10-second observation. So obviously, if you observe 100,000 stars for 1 hour, you will get some occultations. However, the effect on the photometry, if you see a loss of 1 millisecond over the exposure, which can be of a few seconds or less, you get that the drop on the photometric precision is of the order of millimagnitude, and that is less than the precision that we can achieve from the ground. So that means that, yes, satellites will pass in front of stars, even if they are not illuminated, they will cause eclipses. Fortunately, it does not happen often, and the effect on precision of the photometry is small, so it's also not an issue. So once you combine all this, this is the kind of table that we are producing for our telescopes and other telescopes. Don't try to read the number, they're not relevant. What is important is here in X, all these columns are represent different elevations of the sun. So from sunset into the twilight and finally into the night until you hit midnight, depending on the season, and for various types of instruments. So green means the effects, the losses are negligible. Gray, yellowish means that they're below 1%. So that means that we could start to notice them, but it's still tolerable. 3% for us, yellow, is an interesting limit because it is our threshold for acceptable losses. So any cause of loss of the order of 3% is something that we consider a problem. And you see that we have some yellow here. Then red means less than 30%, and dark red here, more than 30%. So you see that these are concentrated around twilight, where the satellites are most numerous, and that the worst case is the ultra-wide field imaging of the LSST camera at Vera Rubin. Fortunately, most of the night and most of the instruments are still protected. But as I said before, there are some exceptions. So let me now spend the few minutes I have left. Do I have a few minutes left? Yes, a couple, on mitigation. And I will go very quickly through the mitigation at the constellation level. You could have less satellites, but I trust that if the operators could work with half the number of the satellites, they wouldn't launch them. As I've seen mostly in the first talk, lower altitude is much better for us, because if you go at lower altitude, you see a smaller fraction of the constellation. They drop faster in the shadow and they are more defocused. And darker satellites, which means better design, and Starlink has done a lot of work on that, and better operation to try to hide the solar panel or to change the orientation of the satellite to minimize the effect. There are also a lot of things that can be done at the policy level. It has been discussed partly yesterday. We will have a talk by Juliana later today and by Connie Walker about the IAU Center for the Protection on Dark Skies later today. So stay tuned. At the observation levels, there are things that you can do. Basically, avoid the satellite, avoid the contamination. And you can do that first in a deterministic way. That means you need to know where the satellites are to avoid them. And you can do that using a database of orbital elements and compute the position of everything and try to see what can be done. I think Jeremy is going to talk about that right after. But there is another way which is also kind of promising, is to put a little camera piggyback parallel on the telescope that controls the shutter of the camera. And so basically, if you are observing a field of view and a satellite approaches, you detect it, you close the shutter, let it go through and reopen the shutter. You have lost half a second or 1 second, but you have not lost your exposure. Another way is to use a statistical tool, knowing the architecture of the constellation. Basically, it's these maps which give you the density of satellite. And if you look at the scale, just by pointing at the right place at the right time, you can have no satellite because it's in darkness. Or even if there are satellites, you can get a factor of 10 better than shooting at random. So that is going to help also. In terms of data processing, once you have a trail in your data, you can try to remove it or to flag it. It works mostly for imaging. For spectroscopy, it's a mess. And it does not fix everything. The good news is that it is something that we have a lot of experience with. Masking things in the data is something that we have to do frequently. This is an example of asteroids in a Hubble field, but it would work the same for satellite trails. I work on asteroids. For me, the wiggles are the interesting part, but for cosmologists, they are a nuisance, so there are ways to remove them. Yes, and we have a talk about that just after. So to conclude on mitigation, you really have to use them all. Any of them taken separately will not protect your observation, so every step will be needed. And I leave this as a summary of my talk. So to summarize, the summary is the impact on optical observations. It depends. You can have quite strong impact, fortunately, on limited cases like the LSST, mostly at twilight, they can lose up to 30%, or twilight observation, like the example from Alain Maury. The effect will be significant, so that means at the order of 1% loss for wide field imaging and spectroscopy at twilight. It's much smaller for traditional imaging, and then finally, no impact at all in deep night with the issue of high altitude satellites, but also for high-res spectroscopy, occultation, and thermal infrared. All the numbers I quote here is assuming 65,000 satellites. In terms of mitigation, all are needed. And remember the strange case of spectroscopy, where it's not as good looking as an image, but most of astrophysics is done with spectra, and there the contamination could go unnoticed. And that's all I have for today.
Thank you very much, Olivier. That was a great summary. And also, I've just realized, welcome to Piero Benvenuti in our audience. We're honored.
Hi, Piero.
Okay, so we were next to have a talk by Federico di Vruno to cover the impact of satellites on the radio astronomy side of things. Unfortunately, I got a notice this morning that Federico can't be with us. However, he has recorded a clip to cover his subject. If his clip is shorter than the slot, then maybe we could have an impromptu question and answers before we go to the break at 25 to 2 BST. So, Martin, if you could run the talk that Federico sent.
Hello everyone, my name is Federico di Vruno and I'm the Spectrum Manager at the SK Observatory. I'd like to start by thanking Paul and the FAS for this invitation. If you're listening to this recording, it means that I could not connect live, and my apologies for that. You can reach me in my email here for any further discussion you want to make. Sorry. I will be talking about large satellite constellations and their impact on radio astronomy. Because the effects on radio astronomy required a bit of background, I will start trying to answer these three questions first, and then going into the impacts to finalize with some possible mitigation strategies. So let's start with the first question of how is the radio spectrum used? Many systems use the radio spectrum either for communications, for conducting measurements, for detecting positions of objects, or exploring space, etc. It did not take long for people to realize that the radio spectrum is a limited resource and that it needs a clear framework to be sustainable. The International Telecommunications Union is the agency responsible for the regulation of the use of the radio spectrum internationally, and it has divided the spectrum in small bands and allocated them to different radio communication services. As you can see here on the right, this is a typical table of frequency allocations, and it goes from 9 kilohertz up to 300 gigahertz, where the different colors represents different radio services. Radio astronomy is identified as a passive service by the ITU and has allocated some very important bands to it. In this chart, radio astronomy is represented by the yellow color, and if you have very good sight, you can see some of the radio astronomy allocations in. So we know that there are different bands in the radio spectrum assigned to different services. And now it would be interesting to understand how a radio telescope works. In a very simplified way, radio telescopes are systems designed to detect radio signals coming from space. These signals can be billions of times fainter than normal communication signals, and whose frequencies are defined only by natural processes. So in terms of antennas, a radio telescope can be a single large dish with hundreds or even 500 meters of diameter, the largest one, or, for example, an antenna array or a low frequency array. There are many different possibilities for antennas in radio telescopes. As receivers, modern radio telescopes use digital backends, which allow them to channelize large bandwidths for further processing, but there are still some applications which use total power detectors, such as bolometers. And the last characteristic we can mention is that radio telescopes rely a lot on the protected radio astronomy bands that we were talking before, not only to do very special observations in there, but also to use them as calibrators, as they are reliably clean of interference. In addition of using these bands, wideband receivers allow opportunistic observation in other frequencies which are necessary for many science cases. So let's talk a bit about interference. We said that communication signals can be billions of times stronger than cosmic signals, cosmic sources. And radio telescopes normally use very wideband receivers. So this will normally result in very strong signals being received by the telescopes at the same time as the cosmic signals. So what can we do to cope with this or to avoid it? First, radio telescopes minimize the effect of interference by having a very, very large gain towards the sky in the desired direction where the sources are being measured or tracked. And this causes interference signals or RFI to normally being received through the side lobes of the antennas, where the gain is much lower. Some radio telescopes even have a very, very special protection known as radio quiet zones, and these are areas where by national legislation the use of the radio spectrum is restricted to minimize interference into radio telescopes. Of course, there is a special situation with respect to airplanes and satellites, as you can see and you can imagine, as you can see in this picture, where they can appear in the main beam of the radio telescopes and their signals can be very strong. So let's focus now for a moment on satellites and on satellite constellations. Satellite transmissions are not a new thing for the astronomy, but the reality is that before there were not so many satellites in LEO, meaning moving rapidly in the sky, and most of them were in geostationary orbits, at least at some frequency range. As you can see in this simulation of the sky in azimuth and elevation seen from South Africa, before Starlink and OneWeb, there were about 120 satellites moving in the sky, apart from the ones in the geostationary orbit. And now the situation is changing drastically. As you see here on the right, this is a projection that shows 5 of the proposed large constellations that can result into almost 2,000 satellites above the horizon in any moment in time. You can easily think on avoiding satellites on the picture of the left, but in the picture of the right, it looks, of course, much more difficult. And because we are dealing with antennas here, both for receivers and the transmitters, we can consider 4 different cases. The first 2 on the left represent a very high power received by the radio telescope due to beam-to-beam coupling or beam to side lobe of the satellite. Remember that the radio telescope can have a very, very large gain of about 60 dB or 1,000,000 times or more. The other 2 are when the satellites are above the horizon, but away from the main beam of the radio telescope. Now you can imagine that the aggregate of all the satellites above the horizon counts, of course, especially if they get up to numbers like 2,000 satellites or more. And so now that we have laid down the fundamentals, we can talk about the different aspects of radio astronomy that can be impacted. And we can divide this in 4 different levels of impact, with the first 2 being related to the downlinks of satellites and the other 2 as second-order effects. First, if you remember, we said that radio astronomy receivers needs to be very wideband. It is a consequence of this that the downlinks of satellites will fall within the receiver bandwidth, and this will be the first effect. Second, some protected radio astronomy bands happen to be very close to satellite downlinks, and the out-of-band emissions of the satellites could impact the protected radio astronomy bands. The third effect is related to unintended radiation from the satellites, and this is completely separated from the intended downlink signals. And the fourth is the probability of creating a reflecting layer for terrestrial transmissions that could make the transmissions bounce and reach the most remote radio telescopes. So let's start by the first case. And this first case has 2 aspects. First, the probability that the receiver is saturated by the high power received from the satellites. And this is a very bad situation, of course, because in case of saturation, all the information in the band is lost, not only the one where the satellite transmissions are. But this only happens during the time that the satellite is directly in the beam of the radio telescope. So of course this depends on the type of radio telescope and the beam width and the gain and the density of satellites in the sky. So for example, in this figure, the blue curve represents the instantaneous power received by a radio telescope, considering only the Starlink phase 1 constellation. And these big spikes that you see there are when the satellite goes through the beam of the telescope. And the second aspect of this one is that the average received power by a radio telescope can be affected by these very strong sporadic signals, and this will make it much more difficult to conduct these opportunistic observations in frequencies in or close to the satellite downlinks, where up to now this is still possible as long as one avoids the geostationary arc. So the second effect is the potential interference on the protected radio astronomy bands. This is related to out-of-band emissions, and any real signal has a spectrum that looks something like this one in the picture. Of course, this is a representation, right? With its intended bandwidth and then some sort of roll-off with less power as you get away in frequency terms. As you see in this table, many frequency ranges are proposed for satellite constellations, and some of them are already in use, and all of them have a protected radio astronomy band adjacent, meaning right next to it or nearby. The level of out-of-band emissions, the characteristics of the antennas, the constellation parameters, and the satellite density play a key role in defining if there will be interference or not. As one example of these situations, we can consider the 10.6 to 10.7 gigahertz band. This is a radio astronomy protected band, which is adjacent to the currently deploying Megaconstellation downlinks. Starlink and OneWeb have studied compatibility between their systems and radio astronomy in this band and concluded that their lowest channel could not be used. And this technique is normally referred as a guard band. So they leave some space between their downlinks and the radio astronomy band, space in frequency terms. This study was carried out by CEPT. This is the Regional Spectrum Management Organization for Europe, and considers Starlink Phase 1 and OneWeb Phase 1. It is expected that they will update this with their second generation constellations, which will use the same frequency range. Also, it will be important to encourage other operators to do the same. And all the other frequencies which are planned also have radio astronomy bands adjacent, and so these studies will be needed too. And now moving on to the second order effects, let's talk a bit about unintended electromagnetic emissions. Any electrical circuit will generate radio emissions. These are normally very low on level, and in the case of satellite systems, these are only considered if they happen to coincide with the receiving antennas on board of the satellites, so that these emissions do not interfere with the satellite's communications. But what happens in this situation if all satellites in a constellation have a radiated emission in about the same frequency? And what happens if this frequency happens to be at the radio astronomy protected band? So some preliminary studies have shown that radiated emissions control on a satellite constellation would need to be much stricter with the size of the constellation, and in some cases even stricter than the emissions that are required for military equipment going into space. This effect at the moment is not considered in the ITU regulation, and so it requires some further study. And the last effect is the reflections from the ground, from ground-based transmissions. Many radio telescopes have measured bounces of radio signals in large structures, such as airplanes or the ISS, and there are lots of publications about this. And there are studies ongoing to understand how this effect of having many satellites in LEO could create the same effect. And to finalize with this, I would like to go through some mitigation strategies, or what things can we do. On the radio astronomy side, the situation with satellites is not new. Only the scale is much larger. But many of the existing software that can be used or adapt to this new situation. RFI processing can also be used to mitigate the problem. And by using interferometers, for example, with long baselines, the issue can be mitigated even further with when radio telescopes use very long baselines. The new IAU CPS, the Center for the Protection of the Dark and Quiet Skies from Satellite Constellation Interference, apologies, which Connie Walker will be talking later about it, would be an ideal place to develop further studies, observations, software, and policy proposals towards mitigation. Also including the interaction with satellite operators to discuss possible mitigations on their side will be very important. As mentioned before, also national regulation groups have conducted some studies on how to protect some radio astronomy bands, and it will be important to keep encouraging these studies in these groups. And at the national level, some radio administrations have included special protections for radio astronomy stations in the license for satellite constellations, and this is showing how also countries at the national level see how important it is to protect some very specific radio astronomy sites. Okay, and this is just to finalize as a summary of this talk. So radio astronomy has been dealing with satellites for a long time. So this is not a new situation, but the situation is that the very large increase of numbers is producing a new situation, especially for some frequency bands. As we discussed, regulation covers some of the aspects, but more work is needed in the regulation and some things that are currently not covered by the regulation, but perhaps should be. Individual countries are including protections for the telescopes, and some second-order effects are not very well studied or understood yet, but it's important that we do study them and see if there are a very big risk or not. And to finalize, I think the interaction with industry is very important to find possible mitigations in the short term. And with this, I finalize. So thank you very much for listening, and hopefully you have some questions. And if I'm not there, there's my email, and you can contact me. Thank you very much.
Okay, so Federico did say that he would try to get into the Q&A later on this afternoon, I think at 5 to 3 BST. There's a family matter he needs to deal with, so he may be in a position to connect, and even if it's only by phone. Does anyone have any questions about Federico's talk that maybe one of the other astronomers here could answer? Any specific ones? If so, put them in the Q&A. Maybe since we're ahead of time, Martin, we could start to work down some of the questions in the Q&A, and maybe those people who are here can jump in and answer them.
Righty-ho, okay. Did see one. Okay, from Gary Farr regarding Harry's talk, actually. Thank you very much for the excellent work and analysis, Harry. I think this will be very useful as for a comparison between satellite service providers and successive generations of constellations. I believe this work will be of use, should be a use of influence to companies and agencies to improve their environmental impacts in the future. Sorry, that was more of a comment than a question. Yes, the next one, actually, these things stand still. Also from Gary, for Olivier, this is a real problem for NEO, near Earth objects, detection and survey. Seeing what a potential disaster this could lead to is critical that interference is eliminated. So I guess we're talking there of the actual interaction between that and the satellites.
Okay.
That is about it on questions.
So near-Earth objects. The situation for near-Earth object is essentially almost as bad as the image of the comet I've shown. Slightly better because they cannot observe that low, and slightly better because the field of view is smaller than the image of the comet. Nevertheless, yes, they are going to have many trails in the image. However, a trail in an image does not mean that the image is lost. It means that you lose a fraction of the image. And so that means that yes, the efficiency of your survey for near-Earth asteroids will go down by, let's say, 1% or even 5%, which is annoying. However, that is currently not the limiting factor for us to find asteroids. I would say that if we really consider that this is a big issue, we need to have more telescopes looking for these near-Earth objects to explore the sky deep and wide enough. And the fact that we are going to lose some percent of these observations is annoying, but it's not a showstopper for that. Yeah. So, in other words, yes, all observations will be affected, but again, the observations that are going to be destroyed by these satellites are fortunately very small. In most cases, the observations will still be valuable, minus a few percent.
Thank you. Do you want another one, Paul?
Yes, certainly. Yes.
Okay. Does the fact that telescopes are tracking in R&A, RA and DEC have any impact? Presumably the satellite trails change angle from a static position, static situation. That's from John Merrill.
Okay, the answer for that is really easy. No, it makes no difference because the satellites move so fast that the fact that the telescope is tracking or not is completely irrelevant. Remember, in right ascension, you track 1 hour of time per hour of time, just because you follow the rotation of the Earth. 1 hour is 15 degrees, so 15 degrees per hour. Satellites move 60 degrees per minute. So it's really so fast that the motion of the stars is not relevant.
Okay, thank you, Olivier. I think Martin, we can go into our break now, and we're back at 13:50 to hear the first of Jeremy Treglow and Reed. That's giving everyone a chance to make another cup of tea and open another packet of biscuits. And our next speaker is Jeremy Treglow and Reed from the University of Antofagasta, if I've pronounced that properly. And I'll hand you over to Jeremy now.
Hi there, everyone. Yes, I'll start sharing. Can I? Yeah, share screen. Sorry, just 2 ticks. Okay. Sorry, 2 ticks. Sorry. Okay, can you all see my screen okay?
It's still updating. I can see the screen, but it's the preview rather than the actual slide. That's better. Yes.
Yeah. Okay. It's the full screen. Okay. Well, thank you first of all for inviting me to give this presentation. Basically, I'm Jeremy Treglow and Reed. I'm a new junior member of the faculty of the Institute of Astronomy and Planetary Science at the Universidad de Atacama. Prior to that, I was a sponsorship postdoc at the Universidad de Antofagasta. Prior to that, I was a NASA postdoctoral program fellow at NASA Ames, where I was doing work with Kepler. My main PhD research at the University of Kiel was with exoplanetary systems around active stars. But over the years, kind of, especially since 2019, with the launch of Starlink, I've now kind of moved into the satellites and their impact on the night sky. So back in September, with everything that's going on, we founded the CLEOSat group, or the Chilean Low Earth Orbit Satellite Group. And currently we're composed of around 22 members from a range of Chilean universities, institutions, and observatories. Obviously the Universidad de Atacama, Universidad de Antofagasta, some people from ESO and ALMA, and a few other universities across Chile, including the Light Foundations and Protection of the Dark Sky people. Because the impact of low Earth orbit satellites, especially onto the night sky here in Chile, where we've got some of the biggest observatories, and we've got the new telescopes, the ELT, the giant Magellan telescopes, the 30-meter telescopes, also the Vera Rubin. Chile is disproportionately affected by these satellites and by the impact of these satellites. So basically what we're trying to do is try and work out, assess the true impact, develop the models, develop forecasting code software to actually then say how much of an issue it is, who's it affecting the most, and what sort of mitigation strategies can we all develop in partnership with some of these operators and satellite operators to try and minimize the overall impact, not just to astronomy, but to also the ecological impact and potential impacts to cultural and spiritual beliefs, peoples who use the night skies for their storytelling and so on and so forth. So when we talk about low Earth orbit mega constellation satellites, the two that normally spring up are Starlink and OneWeb, though they're not the only ones. We've got the Chinese constellation, we've got the Amazon constellation, and loads of others coming through. But the main important issue with them is basically they're in the low Earth orbit. So for Starlink, we've got orbital heights between 340 and 550 kilometers, while OneWeb, we're close to around 1,200 kilometers. However, the main thing is that the benefit from these satellites to provide global communication, internet services, and to provide high-speed, low latency internet communication to communities that don't have access to high-speed fiber. That is particularly true here in Chile, where we have a large number of remote rural communities and schools who don't have access to high-speed internet. And by providing these services, it can increase the ability to provide top-level education to the children, also allows connection between the communities. And it just generally is an important thing here in Chile, hence why the government is very excited and happy to approve the Starlink ground stations and start things working. One case study that was in the local papers, there's this small hamlet, I think we'll call it, of about 10 houses. While individually they can't afford Starlink, they all clubbed together and brought a dish for themselves, and they share it. So they get about 100 meg in total, and they've basically got 10 meg bandwidth each, which I remember doing my PhD with the broadband with post office at only 8 meg. They got slightly faster internet than I did when I was doing my PhD. So, it's very difficult to convince the general public that this is a bad thing. And at the end of the day, we're not trying to convince the public that it's a bad thing. We're just trying to say, yes, this is great, but there are impacts and there's unforeseen issues that we need to work on so we can all share the night sky together. So, bit of a recap. Back in 2019, basically when the first set of Starlinks were launched, basically both amateur and professional images were contaminated. Here on the right, we got the image from the Blanco 4-meter telescope, the infamous image with about 19 Starlinks satellite trails passing through. And here on the left, we got the image from Daniel Lopez of Comet Neowise. Basically, again, it's been photobombed by all these Starlink satellites. So what are the two primary issues to optical astronomy and basically the quality of the night sky? Well, the first one is basically their reflective brightness. Once they're on station, they have a visual brightness of around about magnitude 5, and that's a stationary magnitude brightness. So basically, if it wasn't moving, it'll be as bright as a magnitude 5 star. But because it's a moving target, the flux is spread or smeared over your detector pixels. So why is that? Well, first of all, the main reason is their orbital heights. As I mentioned before, Starlink's are around about 550 kilometers, OneWeb 1,200 kilometers. We've always had satellites for the last few decades, but most of them, as other people have mentioned, they generally were in geo or geostationary orbits, which have an orbital height of around about 20,000 kilometers. However, at LEO, the satellites are effectively 40 times closer to us. And so using the inverse square law of flux, we know that they're approximately, if it was the same satellite, it'll be about 1,600 times brighter. And this basically can make satellites in LEO orbit visible to the unaided eye at magnitude 7 or fainter. And when I say magnitudes, so magnitude 6 and 7 are probably visible in pristine dark sky conditions like you'll find here in the Atacama, and probably more like in cities like Manchester, or Birmingham, or London. You're probably looking at magnitude, you need at least magnitude 3 or brighter to be able to see, if it's not cloudy, that is. So the other issue is basically the satellites, because they're range dependent, the brightness, they basically become drastically dimmer as they approach the horizon, unlike stars where basically it's the same magnitude if it's looking at local zenith or down to the horizon. However, as the satellite moves, from local zenith to the horizon, the range increases or the distance increases. And that's basically just due to how the orbit is perceived from the point on the Earth that you're making the observations. The orbital height is basically the closest distance between the observer and the satellite, where the range is equal to the orbital height when the satellite is at local zenith, i.e. directly above your head. However, as we then start moving further down to close to the horizon, they do effectively get dimmer, but the number of satellites that are potentially visible increases. And that's because we're now looking for a thicker section of the orbital plane. And so therefore the number of satellites passing through that section will increase. Hence, yes, they're dimmer, but there's a lot more of them. Basically, if this can be seen, this was a nice graphic here from Olivier, his 2020 paper. So basically, if we have our observer or observatory here, the orbital height is basically the range to the satellite is equal to the orbital height when it's directly above our heads. And as the satellite moves across its orbit, the actual distance to the satellite increases. So basically, while the satellites appear fainter at low elevations, the numbers increase. And that's what the point I was trying to make in the previous slide. So what is the benefit of having satellites in low orbits? Because as we've got OneWeb in 1,200 kilometers, Starlink at 550 kilometers, and Starlink has applied for FCC approval to reduce the orbital height. And that basically was borne out by work between Starlink and basically people at the Vera Rubin Observatory and astronomers. But by placing satellites in lower LEO orbits will make them brighter, which is a bit of a bad thing. However, with lower LEO orbits, the satellites spend longer time within the Earth's shadow. So here, if you see on the graphic here on the right-hand side, if the satellite is at a lower orbit, it will enter the Earth's shadow at an earlier point. So basically, the amount of time that the night is affected by these satellites is reduced. While that doesn't help with near-Earth object work and people who require to do the observations during twilight, this does mean that the larger proportion of the night sky, time-wise, will be less impacted by the satellites. So basically, since the publication of various reports, for example, Jonathan McDowell, and consultations between the astronomical community, Starlink has requested permission from the FCC to set the maximum orbit height of their LEO satellites to 570 kilometers. So while that reduces the amount of satellites, the amount of time in the night sky that the satellites are visible, it does make them technically brighter. So the other issue with these satellites, unlike iridium flares, where basically you get very bright light for a few seconds and it disappears, that's basically specular reflection from the solar panels. And so basically when the solar panel comes at an exact angle, they become very bright, but as the satellite moves, the angle, you're no longer at the specular reflection angle, and so therefore it fades away. With the bodies of low Earth orbit satellites, because they're so close, what we're receiving is diffuse reflection. And as you can see from this figure here, basically you get your incident wave. For specular, you just get it directly reflected. However, with diffuse reflection, it's reflected at multiple angles, though at lower intensity. Now, by orientating the satellite in a certain position, you can have the solar panels reflect the reflected specular light away from the Earth. So that should not be much of an issue, though that there are glints and other things taking place. However, So basically, that's why the satellites are basically visible from horizon to horizon, because we're not just looking at one particular reflection angle, we're actually looking at the entire diffuse body, which basically means we need to take into account solar phase angles. And so when we talk about phase angles, there's three components. There's the main component where basically you're looking at your satellite. So you're looking at your satellite, you've got the sun at an angle below the horizon, and you're basically calculating the angle between the vector from the satellite to the sun and the vector between the satellite and the observer. And that's just quite simply the angle between the sun and the satellite from the observer's position subtracted from 180 degrees, because the sun can be taken as affinity. And so therefore it's just basically it's 180 degrees minus the 180 degrees is the sum of the two angles. However, this then can be, this phase angle can then be broken down into two separate smaller angles, which we call the solar phase angle and the observer phase angle, where for the observer phase angle, it's basically the angle between the unit normal from the bottom of the satellite to the nadir point on the surface of the Earth and the observer. And so basically this angle can be quite simply calculated by basically taking the ratio between the distance between the observer and the nadir footprint of the satellite on the Earth, divided by the orbital height times by sine alpha. In this case, it's basically the elevation angle where the horizon is 0. And from that, we can then basically calculate the phase angles. So, you know, nice geometry. However, for the solar phase angle for the satellite, if you see that this is the satellite SASIS, basically we have our sun angle. Basically, we've got our unit normal pointed towards the Earth, or where the nadir footprint is. And if we look at this section, basically where the satellite is, where basically the satellite is directly above the Earth, basically we can calculate that the solar phase angle is quite simply this angle here, which is equal to the sun being at infinity, is basically equal to the sun's elevation angle at the point of where the satellite is. And so we can see from this simple diagram that basically the two angles sum up to 90 degrees. So again, we can then calculate the solar phase angle. So we can then calculate the solar phase angle theta and the observer phase angle phi. And basically the main phase angle that I was discussing earlier is basically the angle between the two vectors. So, sorry. So because we're dealing with a diffuse body, we've got basically microfacets, which are basically irregularities and smoothness of the material. We have different materials. And so basically in optics, quite a lot of people talk about the bidirectional reflectance distribution function. And basically this is a function of four real variables that defines how the light is reflected on an opaque surface. So we get into lots of complicated, well, not too complicated, but we get lots of mathematics where basically we've got the surface point, the lighting direction, the viewing direction, the half angle vector, the microfacet normal distribution function, the shadowing term, the confidence function. I mean, then we've got basically the domains covered by the partial NDF tuple, and it gets quite complicated. However, we are able to measure these properties. Generally speaking, they're done in the lab by the satellite operators. They shine different light sources at different angles with different cameras at different angles to measure these properties. And from that, you can then design your BARDF model. However, as astronomers, we don't have access to these satellites in the lab. We have to do these observations from the ground using our telescopes. And you may ask, why is this important? Well, as I said before, the satellite, the brightness or the reflective brightness of the satellite is dependent on the phase angle because it's a diffuse surface. So if we want to model this, so we can then turn around and say, aha, a satellite 52 degrees north from our location should have a reflective magnitude of the N. So by actually be able to collect multiple data sets of all the satellites at different phase angles, ranges, we should, in theory, using Bayesian methods, be able to fit different BRDF model parameters and try and get some sort of insight into actually what's going on, what's causing the brightness, which parameters has the greatest impact on the brightness. And so hopefully be able to actually model and predict how these satellites are going to behave in terms of brightnesses as they pass over our field of views or across the night sky. Now, phase angles are quite important, and work is currently going on at the moment. But basically, if we collect observations of satellites for a range of phase angles, we can begin to fit different models of the data. A good recent example was from Boyle earlier this year, where basically they used a diffusing sphere model and a heuristic power law, or the STO, or phase angle. And basically, they fit the data here is basically the black circles and black squares. I can't remember. These are Starlink satellites. One's with visors and one without. And the red data points is basically the diffuse sphere model, while the blue is the heuristic powers law models. As you can see, it's generally a good fit to the data they collected. However, we do get these anomalies where basically we don't know what's going on. The model can't account for these situations. And so basically what we're thinking of, what we're thinking here in Chile is that the satellite's attitude is different, i.e. the orientation of the satellite. It's not, so basically satellite 10 here is at a different orientation, satellite 22, therefore we're looking at a different surface, and therefore and different microfacets depending on in the surface, and so therefore the amount of light it reflects in our direction is completely different to the other positions. So can we begin to understand all of this? Well, technically speaking, if the three main components to the satellite's brightness is its range, the phase angles, and now the orientation of the satellite towards the observer and the sun, then we've got three things that we need to be concerned about. The range is not that difficult. We can calculate that and using the square law, we can adjust the magnitude accordingly. The phase angles, well, we know how to calculate them, but we still need to work out how they actually play, how they actually impact the brightness. But that's then complicated because we need to know the attitude of the satellite. So some of the work that we're now starting to do here in Chile is we're now starting to perform simultaneous multiband observations in both the optical and the near-infrared. The image here on the right-hand side is a test image of Starlink 2362, which we obtained with GROND on the ESO MPG 2.2 meter telescope in La Silla. GROND is a gamma ray burst detector, and it's got basically, it's got two cameras, an optical camera and a near-infrared camera. The optical cameras can basically observe simultaneously in Sloan G, R, I, and Z, and also in the near-infrared JHK. And basically in this set of images, it's exactly the same image. As you can see, the stars are in the same positions. The optical are about 5 by 5 arc minutes, while the near-infrared's 10 by 10 arc minutes. So basically, this small little dot here is basically this basic star here. And basically, in each of these images, the satellite is at the same range, same phase angle, and same orientation. And so basically what we can then do is we can start looking and analyzing the color index of the reflected light. And when we say the color index, we're talking like magnitude B minus the magnitude of the object in V. And this is basically what we help do to characterize stars. So basically, you know, red dwarfs will basically have a will basically be brighter in the V, therefore the BV will be negative, while for blue stars, the star will be brighter in the blue, and therefore BV will be positive. So because we're dealing with reflected sunlight, then we would expect the color index to be the same as the sun. So basically what we're hoping to do is make these observations and make comparisons of the color index of the satellite to that of solar, or to that of the sun, and try and see if we can see any deviations from that, which could potentially give us insights into the angle of the surface or particular type of surface of the satellite we're examining. And then once we've done all of that, once we get enough data, we can then start using a bit more complicated BRDF models, such as the reflected, basically such as the Beckman distribution, or a spectrally varying bidirectional reflectance distribution function, which basically says you have a BRDF function, but its properties are different depending on where you are on the object. And that basically helps us measure the microfacet density, or basically the smoothness of the reflections. So smoothness of the reflected surfaces. So the work we're doing, basically, to collect all this data, we basically need lots of telescopes and lots of data. We currently have access to 2 telescopes here in Chile, the Chicana 0.6 meter telescope at Koriyama, which I'll be discussing in a bit, and the Danish 1.54 meter telescope at La Silla. We also have access to the Caja 1.23 meter telescope in Colorado, Spain, and we also got access to a telescope in Korea. And hopefully later this year, we should be gaining access to a new telescope that's being built at the Quang Hon Observatory in Vietnam. And basically the idea is to measure the brightness of these satellites, brilliant, but also to see if we can measure any geographical differences in the brightnesses. So if we got the same range and same phase angles, is there any major changes in the satellite brightness if we're observing them here in Chile or observing them in Europe due to different latitudes or different longitudes due to different orientations of the satellites based on the ground stations and other stuff? We also plan to use this to measure the accuracy of the TLEs. Again, I'll come to this later, and I'll be coming to this later in the talk. So we're getting some great observations at the moment, basically from the Kaha 1.2 meter telescope. We did some observations of Starlink 1436 or VisorSat, which was the first Starlink to have visors. And also we did some observations of non-visor Starlinks at the time. And basically we also did some observations of the OneWeb satellites. Now, bearing in mind that after the 9th launch, Starlink started adding visors to all of their satellites. However, from what we can tell now is now they started using the onboard communication lasers between the satellites. They've now removed the visors. So we have got observations starting up next week. So hopefully we'll be able to see if there's actually what difference that has made. But basically for the VisorSat observations, what we found is basically, oh, I think some slides are gone. Okay, basically what we found was basically basically when we get the observed magnitude, and basically that's the magnitude of the satellite at that image. The calibrated magnitude is when we calibrate for range and bring it to 550 kilometers to allow us to do fair comparisons between these satellites. At the top here, we've got our observations of DarkSat, which we completed a while ago, back in 2020, before everything shut down due to the pandemic. And then more recently, our observations of VisorSat. And basically what we see here with VisorSat, we've got a magnitude of about 6.4, which is virtually on par with DarkSat at 6.5. Bearing in mind that these are two different filters, we've got the Sloan G filter and we've got the Cousins V filter. So the wavelength's slightly out, so we do expect some differences. However, they do quite nicely agree within their 1 sigma error. And this basically tells us that VisorSat or the visor designs are roughly on par with the darkening treatment used with DarkSat without the inherent overheating issues that DarkSat suffered from. And also, but what it does also show is that for both DarkSat and Starlink 1113, which was observed at the same time as DarkSat, is that both satellites get brighter towards the near infrared. And basically the effectiveness of the darkening treatment reduces towards the near infrared. Well, our work with OneWeb satellites basically shows that basically this OneWeb satellites have a rough magnitude of about 8.1 in the visible. Now, this is quite important because part of the work that was done in the SATCOM-1 and SATCOM-2 working groups and the IOU Dark and Quiet Skies report is that we need, at least for the Vera Rubin Observatory, which by the looks of it is going to be the most impacted professional observatory at present, is we have a limiting magnitude, which is basically 7 plus 2.5 times log of the orbital height over 550 kilometers. And basically what that means is if the orbital height is less than 550 kilometers, the magnitude still has to be at least 7. So we need the satellite's magnitude 7 or fainter. However, when we start going to OneWeb, where we got an orbital height of about 1200 kilometers, this equates to that we need the magnitude to be at least 7.9 or fainter. And the reason for that is, and you'll be seeing it later, is due to the higher orbital height, the satellites have a lower angular velocity. When I say the angular velocity, it's how many degrees per second it travels across the night sky. So if the satellite's moving slower from our point of view, therefore it's going to spend longer illuminating your detected pixels, and therefore we need them to be fainter so they don't oversaturate the pixels. So our initial results seem to suggest that basically OneWeb satellites are in the safe zone. Okay, so yes. So the work we're also now doing with the Danish telescope, basically we started using it last year. The Danish telescope is basically at the ESO Lucia Observatory in Chile, and is operated 6 months of the year by the Danish community and 6 months of the year by the Czech astronomical community. The Danish operation is basically focused on gravitational microlensing for the detection and characterization of exoplanets. And it's basically organized as an international team called MindStep, or the Microlensing Network for the Detection of Small Terrestrial Exoplanets. And it's something I've been a part of since starting my PhD. And basically we go out, we spend 2 weeks observing as part of the team. And basically we basically track basically newly detected planets from gravitational microlensing. However, for this, we need to make observations towards the galactic bulge. And so basically, during the 6 months that the Danish community has access to the telescope, it's basically between May and October, when basically the galactic bulge is visible from this part of the world. And basically, we do the observations when the galactic bulge is at least 30 degrees above the horizon. So we also do parallel projects as well as the microlensing, and basically they're filler projects. They're projects to do when the bulge is above 30 degrees. And so for last season, that included basically observations of low Earth orbit satellites. The 2021 season began back in May and continued through to September. However, we did have technical issues with one of the dome motors, which basically suspended all observations for at least 2 months because due to the pandemic still, there was a skeletal staff at ESO, and so even though, at the SEA, and so even though we were able to get the dome motor event a new replacement out there, it took them longer to get it sorted out because there just weren't as many staff. However, during those 4 months of observations, we observed over 700 Starlink and OneWeb satellites across the U, B, V, R, and I passbands. As we can see here, we've got a table here of just the total number of observations. We've got over 100 observations in the U band, which is basically around 350 nanometers. We do have a lot more in the R band, and that's just quite simply because when we're doing the observations, we have 2 cameras, so you have to do 2 sets of sky flats. And if in the evening there's a bit of cloud, you can't do the flats. And so basically what the observers tend to do is say, okay, we've got an exoplanet transit we need to observe in this passband. We'll just do flats in that one passband and do the satellites in the same passband. So that reduces the amount of work they have to do, which is fair enough. But basically, our postdoc, Christian Adam, did an initial analysis of just 50 V band observations of OneWeb satellites, not the 80 that we got. Did a range correction, and basically what we find is roughly 54% of them are technically in the safe zone, whereby they're at least magnitude 7.9 or fainter, while 46% of them are still brighter than magnitude 7.9, with some around the magnitude 6.7 mark, 6.8. And that's for a range of orbital height of 1,200 kilometers. So basically we reduced that down to 600 kilometers. They're basically twice as close, therefore 4 times brighter. So there's still a lot of work to do. Obviously, this doesn't take into account the phase angles. This also doesn't take into account the orientation of the satellite. And so we still have a lot more work to do in this area. However, the work we have been done so far is basically we have a publicly accessible satellite tracking code available to help plan observations of both Starlink and OneWeb satellites, which is on our group's GitHub page. Oh, no. There we go. Basically, it's available here. It is written in Python. So obviously, any of you who aren't proficient in Python or don't want to do computer coding is perhaps not ideal for you. However, what we have done, we've written it in such a way that you don't actually need to know how to code. You just install Python or you install the dependencies, and you can then just basically run the software just by typing Python satellite tracking, and it does it all for you. So it does make things a bit easier in that regard. However, work is still ongoing by our postdoc, Christian Adam, at the Universidad de Antofagasta, who's been funded by an ESO regional funds grant, and my PhD student, Maria Isabel Romero, here at the Universidad de Atacama. She's been funded by a grant from the US Air Force Office of Scientific Research. And at the moment, they're working on developing a data pipeline to perform image calibrations, flat bias, dark subtraction, perform astrometric calibrations, automatic streak detection, and magnitude measurements. However, the work's still ongoing, but some of the work they've basically done the calibrations and the astrometric calibrations. And the astrometric calibrations basically just say, okay, we know what these 2 stars are, and then orientate the image and shift the image to make sure that everything's in the right place. This work will be available to the community at some point in the future. Obviously, it's all in Python, so as I said, it might not be suitable for the amateur community. However, we are hoping at some point to make everything more web accessible. So hopefully, we can remove that remove that barrier. So that's most of the that's regarding satellite brightnesses. However, as an optical astronomer, I do mainly work with exoplanets, we like to do our observations both in the optical and near infrared. And so the issue is how does the brightness of these satellites change regarding different wavelengths? So back in 2020, before everything shut down, we were able to get some observations done of DarkSat and its sister satellite 2113, which I mentioned earlier. Basically, we used the Chicana 0.6 meter telescope at Koriyama Observatory, which is owned and operated by the University of Antofagasta. And this is an aerial drone photo of the area. It's a lovely area. It's beautiful. And also with our friends at ESO, we were able to get some images of the near infrared in the J and KS bands with the Vista 4.1 meter survey telescope. And so basically, with Koriyama, we did the optical with the Sloan G at 475 nanometers, Sloan R and Sloan I, and also with the near infrared, the J bands 1.25 microns and the KS bands 2.15 microns. And so basically, what we did, kind of what I showed earlier, but basically what we found was that basically the standard design had an on-station stationary magnitude of 5.5 magnitude, while the first attempt by Starlink to reduce the reflectivity, DarkSat was basically in the visible about 6.5 magnitude, so about 55% fainter, which is a step in the right direction. It doesn't solve the issue, but it's a step. Also, then Starlink reported that they had issues with heating issues due to the darkening treatment, which caused some issues. Hence, they went into using visors. But our work, though, shows that the reduction in the near infrared was only around 28%. So when we look at basically the reduction of the reactive brightness here in the Sloan G and R, we're around about 50%, but as we move into the near infrared, we're less than 30%. And so basically, for DarkSat, it was around around magnitude 4, while for the undarkened satellite, it's around 3.6. So we're only talking about 0.4 magnitude change, so 1 magnitude. Now, this does cause a bit of an issue because basically we do a lot of, especially deep field galaxy work. They do a lot of work in the near infrared. And basically, because the satellites get brighter towards the red wavelengths, this makes them brighter in the near infrared and can cause issues. So one solution here is to apply a dithering technique. Basically, this is just an image from the Vista telescope where we have 16 detectors, but we have gaps in between them. And the idea is you take an image, it dithers slightly, takes another image, dithers again, takes another image, dithers slightly again, takes another image, and you then combine them all, and all the gaps are in between are filled, and basically multiple sections are observed more than once, and basically create a single image. This does have a great ability in that, for example, from Detector 11, one of the single footprint images has the DarkSat traveling across it. But when we combine it with the other 3 differing images, we actually kind of almost remove the satellite streak. So by dithering, we could potentially remove the issues from these satellites. However, these were 30-second exposures with 4 dithers, so we're talking about 2 minutes. Quite a lot of the observations of galaxies require 30-minute exposures. So if we're dithering 4 times, you're looking at 2 hours exposure per target. And as you can see, the satellite streak is still quite visible. So if we basically said, okay, let's increase this to 6 or 8 dithers per target, we're now looking at potentially 4 hours per target instead of 2. Now, obviously, it's only dark for about 12, 13 hours a night. So before you'd probably be able to do 6 targets a night. Now you're only able to do 2 or 3 targets a night. Hence, if you want to do that collection of 30 galaxies, you're going to require a lot more many nights. Hence the telescope time allocation committees who actually look at all the different research proposals and allocate time to each one. We'll have to turn around and say, yeah, we've run out of time, we can't do your project, or we can do your project, but only half the sample. And so that's going to have a knock-on effect on the amount of science that we can do per night and the amount of science we're able to do. So while dithering is an initial short term, yes, it can help. It doesn't solve the issue, and it makes things a lot more complicated and a lot more expensive to go further down the road. The next issue we have, obviously, if it's just a handful of satellites, yeah, 1 image here and there, we can get away with that. However, it's the large number of satellites predicted to be in LEO by the end of the decade. I think it's been predicted to be over 100,000. These are some model simulations for Samantha Lawler, And as we can see, when we're looking at basically the satellite distribution from latitude and longitude projection, we've got large numbers of these satellites, and mostly over the US, Central to Southern Europe, Africa, and here in Chile particularly. And this is just a cut section of the distribution over the United States and Canada, because they're because Starlink's is an American company, and that's where they went for it. At the moment, basically, we're looking at over 65,000 satellites have filed at the FCC or the ITU to be in LEO. Obviously, the main culprit is Starlink with about 42,000. Then we've got OneWeb around 7,000. We have the Chinese constellation with about 13,000, and obviously we have Kupia. So, and that's just what we know of so far. Basically, we're taking all the other potential companies with, who said they're going to potentially be filing in the future. We're looking at 100,000 plus, if not more. And so this is something that we're going to have to worry about. Here on the right-hand side is it plays okay. Is an animation from our satellite visibility code that we've done for this evening's twilight at where they're building the new ELT. The red dots represent Starlink satellites, and the blue dots are basically OneWeb, and this is basically from the supplemental TLE. And these are all the visible satellites during this evening's twilight. As you can see, we've got 1 or 2 trains coming across. And basically what this shows is obviously towards the center here, basically we're looking at local zenith, so that's where the satellites will be at the brightest, while here on the towards the edge of the circle is basically the horizon where they'll be at the faintest. And at the moment, we've got around about 2,500 satellites, Starlink and OneWeb satellites in LEO. Basically, if for this evening's twilight, there's going to be about 313 of those satellites will be visible above the elevation of 30 degrees. Now, 30 degrees is important for us in astronomy because local zenith, the air mass is considered 1. When you get down to 30 degrees, the air mass is at 2. And below 30 degrees, the mass increases rather rapidly. And so basically we tend to try and keep our observations at 30 degrees or higher because we don't want, because the atmosphere gets becomes an obstacle. However, when we start looking at, say, all the satellites above 20 degrees, because some telescopes can go down to 20 degrees, there's at least 450 visible over the 1.5 hour twilight window. And if we basically take into account all the satellites above the horizon, then there's at least just under 1,000 of them visible. And this is only with 2,500 satellites in orbit so far. If we do a simple extrapolation of this 2,500 to 100,000, then basically this 313 becomes more than 12,000. And that's above 30 degrees by the end of 2029. Now, obviously, that's just a brute force extrapolation. Depending on which orbits they go in, certain orbits are not visible from certain locations. And so basically, you can't just take that number and extrapolate it to every single part of, in all the observatories across the globe. You need to do these calculations for each individual observatory based on, its latitude and longitude. However, this just highlights the issue that, at the moment is like this. A decade from now, for every dot you see, there could potentially be another 40 dots. So, it's going to be a potential issue, especially as I showed before, we're all looking at magnitude 5, 6s, and 7s when they're at local zenith, and magnitudes 8s and 9s and 10s when they're closer to the horizon. So, okay, as I've shown there, we can go through this code, we can do a calculation, we can do to predict where the position of these satellites are going to be. However, there's this very slight issue with the 2-line elements, which is basically based how the positions of the satellites. As you can see here, you've got an example here of the 2-line elements. One of the things that we're hoping to push for the operators to start using is the orbit mean elements message, which is basically the same as the 2-line elements, but actually gives you the units and actually what these numbers mean. For example, we've got the mean motion of 1.027272, and up here, that's basically the mean motion. So basically, you actually can read this and actually go, okay, I understand what's going on here. What also makes this extra special is basically we have the covariance matrix added to the bottom of the file. And the covariance matrix basically gives us our uncertainty in these parameters. So any of you do science, basically, that, when you have a measurement, you have to give the uncertainty. So because, how uncertain you are that the measurement is exact. Basically, the two line elements just gives us a single data point. It gives us the position in X, Y, Z, and it also gives us velocity in X, Y, Z. And so basically, we only got that one data point and we can only extract a single straight line from that data point into the future where the position of the satellite is going to be in its orbit. If we had uncertainty measurements, we can then actually begin to forecast and actually derive confidence intervals saying, we're 97% certain that it's going to be in this area at this time. We're 67% certain it's going to be in this larger area at this time. And then we can actually begin to actually forecast the positions of the satellites a lot better. However, again, this is a recommendation. There's no way to force the operators to use this. Hopefully they do, but there's no way to force them, especially when you're looking at other countries and other constellations from other countries. And so basically what we're trying to do at the moment is measure the accuracy of the TLEs. So here we've got an image, I think, from the Color Outer Telescope. It's 13 by 13 arc minutes. The center of the image is basically centered to where the satellite was supposed to be at the time of the observation. And we can see we've got the satellite streak going straight past. So when we zoom in, we measure a spectral accuracy of about 0.4 to 1.5 arc minutes. So that sounds pretty close. However, unlike stars, which are static and don't move, this streak is basically a moving target. So basically, it's a position of the satellite as a function of time. We don't know whether the satellite was here at the edge when it was supposed to be at the center or very close to it. And that's basically because, for example, in this particular image, it's a 10-second exposure. The satellite took about a second to pass through the field of view. So the satellite could have been 4 seconds early. It could have been 3 seconds late. We don't know. So to be able to work this out, what we do is we switch to telescopes with larger field of views and perform even shorter exposures. For example, here we've got an image from the telescope in Korea. It's 72 by 72 arc minutes, and it's a 2-second exposure. And basically what we're able to do is capture the start and end point of the satellite streak. By doing this, we can then basically, knowing the angular velocity of the satellite, we can integrate that over the trail length to work out the position of the satellite as a function of time. Basically here on this is an example of basically how we can actually calculate the telescope pointing error, where blue is basically the center of the image, and red is basically where the satellite is supposed to be and where the center of the telescope is supposed to be. And so basically we calculate and make corrections for that, and that's where astrometry comes from. But basically we can then ascertain that the difference between where the satellite is supposed to be and to where it was predicted, and we can actually calculate its distance to be about 18 arc minutes. Okay, brilliant. So we measured the accuracy of that TLE for that particular satellite. However, that doesn't give us an insight on the entire situation. So basically, what we need to do is we need to do this for population. Harry, who spoke earlier, I sadly didn't see his talk, it was just a bit too early for me here in Chile, did some wonderful work with the PROMIS telescope at the University of Arizona, where they basically measured the accuracy of about 567 Starlink satellites. And basically, you've got the number of measurements and basically the angular offset, or the uncertainty between the TLE prediction and where the satellite was. And as you can see, the majority of them are basically less than 0.1 degree, or basically 6 arc minutes. Our image from the one I just showed before is around about 0.3 or 18 arc minutes. And we basically got a distribution up to about 0.5 or half a degree. So by doing this for different types of satellite brands, so you've got OneWeb, the Chinese, GW Constellation, you've got Starlink, and then you've got different populations within that operator brand. So Starlink, you've got the original ones, you've got the ones with visors, and you now got the new ones that don't have visors. So basically, we need to do this for each of these designs. However, there's an additional problem. We basically use the Starlink, we use SpaceX Starlink supplemental TLEs. SpaceX also provides ephemeris files, so does OneWeb, but I think OneWeb are only available to other operators, not available publicly. SpaceX makes theirs available publicly. And basically the ephemeris is basically the TLE that's had some orbital equation, that's gone through some orbital equations and then got the ephemeris out, which is basically the position of the satellite. The code that we use does its own orbital equations and takes the TLE and does the same thing. However, if you notice, the files are released exactly 8 hours, or roughly 8 hours in time. So how accurate is the TLE prediction an hour after its release compared to, say, 7 hours after its release? And if there is a difference, how do we measure it? Well, here on the Earth, obviously, basically, we got different time zones. And so basically, if the TLE is released roughly UTC -3, then basically it's still daylight here in Chile. So by the time we get to make these observations, the TLE is about 2 hours earlier. However, in the UK, if it's released at that time and it's still dark and it's still in twilight, basically you'll be able to do the observations within minutes after its release. And so basically by having telescopes positioned at different longitudes across the globe, i.e. different time zones, we're able to then do these studies for these groups of satellites for different time zones to actually measure the degradation of the accuracy of the TLE as a function of time. And by doing that and combining that with the models, we're basically able to then actually try and create a forecasting algorithm that not only predicts the number of satellites that's going to be in a part of the sky at a certain time, but also combined with our magnitude and BRDF measurements and models to predict how bright they're going to be. And that's probably one of the more important things is, while there's going to be a large number of these satellites, it's going to be very hard to try and avoid them all together. It will allow people to turn around and say, okay, if I want to look, I want to do this lovely image of the Crab Nebula or the Eagle Nebula or the Horsehead Nebula. If I do it during this time, there will be N satellites of magnitude 5 or brighter passing through my field of view. If I leave it 20 minutes, yes, there will be more satellites passing through my field of view, but the brightest will be magnitude 10. And I can get rid of that by doing a different or two. And so, yes, that makes things difficult, but it allows people to at least try and plan the observations to minimize the impacts. At the moment, we're currently, basically, due to the pandemic, everything shut down. Things are now kicking off. We've got some grants coming through this year. We're building up a team. We've got some postdocs, got some PhD students. And basically, the idea is to continue performing new survey observations of LEOsats. Literally next week, we begin new observations with the Danish telescope again. That will continue right through to mid to late October. Simultaneously, we can use the data to measure the magnitude in different wavelengths, and therefore then basically try and construct a bidirectional reflectance distribution function or BRDF model for the different satellite designs. And then on top of that, try and develop a data-driven model and LEOsat forecasting algorithm to forecast the business of and brightness of the satellites. Originally, this is going to probably be a Python code, so it's going to probably be, a bit technical, but we are hoping once we've got the nuts and bolts and the main engine together to apply for additional funding, try and make it web accessible, or perhaps even make it usable via an app on a phone to help people, who've just, gone out for the night to do some, astrophotography, and just so they can work out what's going on. Okay, thank you.
Thank you very much, Jeremy. Do we have any other questions than just Gary's at the moment? Or any comments from any of the other panelists? Okay, I'll launch then into giving a brief talk here. Despite my best mafioso techniques to find someone who could speak on the subject that I'd anticipated for this next slot, I wasn't successful, so I'm afraid you're lumbered with me. I'm going to give a very brief overview of what I'd hoped would be covered here, which is basically to say a little bit about PassPredict and the TrailMask software that's being developed as a result of the SatCon 1 conference. I'm just going to share my screen. Can you see that?
Yeah. Yes, full screen. Great. Perfect.
Okay, thanks very much. Okay, so SatCon 1 recommended the development of this software, and PassPredict was the first I'm going to talk about, to try and give the best estimates of where satellites are going to be at any given time. And some of this has already been covered just now in Jeremy's talk. However, these estimates will be flawed, and they're going to be flawed because there will be observation error in the observations used to determine the orbital elements. So even though you have a lot of observers all around the world, there are going to be radar stations, there are going to be amateurs, there are going to be professionals, all of this data is going to be amassed together, you're still not going to get a perfect set of orbital elements. Not only that, satellites will attempt to avoid each other, or maybe there will just be operational changes in altitude or something like that that will affect their orbit, and so their orbital elements will change. And then there's going to be things like solar activity causing changes to the position of the satellites. So these combine, along with the fact that we don't actually necessarily know how to, we don't at the moment carry the error information in the TLE format, as Jeremy was just saying, so that when you come to predict forward with the two-line elements, you don't know how inaccurate your prediction is going to be, which is part of the reason for the move to this OMM format, which was, I think, recommended by Celestrak, to enable you to predict further forward. Now, I rather liken this to the problem of predicting the position of a hurricane going into the future. And you see this sort of curved teardrop effect, which is where the people predicting the track of the hurricane are fairly certain where it will be in the short term. But as you get further and further along the predicted track, you have less and less certainty. And by the time you get out here, many days into the future, you have even less certainty as to where that hurricane is going to be. That means you don't know exactly where the center of the hurricane be when it makes landfall here. And exactly the same sort of thing applies if you don't know how inaccurate your measurements are, and you don't carry that information in your orbital elements, then you can't predict accurately how uncertain your prediction is in the future. So hence the move, I think. I think there's a lot of pressure for it to move to the OMM format. So satellite operators may provide timely notice of changed orbital elements. And in our talk yesterday from David Goldstein, he was saying that SpaceX recognized that they need to update more frequently, and they will be providing much more regular information. But of course, SpaceX and OneWeb, I'm sure, will be quite cooperative in providing this data. They want to be seen as good operators in the space domain. We may not have as much cooperation from satellite systems being operated by other countries, perhaps Russian satellites or Chinese satellites, where the governments tend to want to keep a lot of information more close to their chest. So maybe they won't be as forthcoming, and we will have to rely entirely on observations that are made. Amateur astronomers can submit valuable position and timing observations to help to determine the orbits. And I know that in the UK, we're trying to get underway a project to involve amateurs in making the position and timing observations as well as brightness observations. So one of the advantages of the ephemerides can be that you can mitigate the effect of satellites by allowing yourself to plan your observations in advance. You choose which particular time slot is best, that satellites are either not going to pass through your field of view, or if they are, they will just clip the edge of your field of view. But this all depends on, of course, having an accurate determination of when the satellite's going to be. It would be annoying to say, this satellite's just going to miss my field of view, and then it goes straight through the middle. So what if, that's all very well and good, where you can try and plan in advance, a sort of a pre-mitigation measure. But what if the damage has already been done? The trails are already there in your image, and you want to try and do something about it. What if you've got a very long exposure and you can't plan to avoid those satellites? Now, I was very interested in the dummy telescope that Olivier was talking about, and this would seem to solve some of these problems, where you maybe aren't relying on ephemerides to predict your satellite in advance, but you can use a dummy telescope which is looking around the area of where your field of view is to close a shutter during the transit of the satellite through your field of view. But we need to find really a way to remove or at least mask out some of the streaks that you will find in the images. The other thing too is that this would perhaps allow us to go back and process images, historic images. So TrailMask is the software that's being proposed for this, and this is based very much on a talk that was given by Morgan Schmitz at the SatCon 2 conference last year. So we need to think, first of all, what do we want to get out of TrailMask? Outputs, first of all, clearly we want images to come out with the trails masked out, removed from there. Removed as best we can. Of course, removal is a word in quotes here because you're never going to remove the effects of the trail completely. And maybe you can't. Maybe the pixels are saturated, you can't recover the information. Maybe the trail is blurred but still too bright, and in that case you've got quite a wide streak that's difficult to remove, but you may be able to at least do something to improve the image, or at least maybe automatically determine that you've got an image that really is for the bin and can't be used in further processing. We also would like to know where the trail is and what area has been used for processing, because any processing that's done isn't going to be applied over the whole image. It's going to be wherever you've determined the streak to be, and then you will analyze it in more detail to work out how best to recover the information. And we would also like to know out of this a list of the individual trails found in the image. So this is a piece of software that needs to be able to batch operate on perhaps a large number of images at the same time, and potentially, of course, more than one trail in an image. One of the things that has to be dealt with also is that you could have a satellite which is tumbling, or a piece of debris that's tumbling end over end like a tumbling rocket booster, and the trail is going to be a dotted image which is going to be wider in places and narrower in places, and therefore you've got to have very good, very adaptive techniques to actually remove the effects of that from your image. So we need to look at what the inputs are going to be. One of them is input images coming in FITS format, and the headers there will contain information such as the field of view, pixel scale, and things like this, but potentially could be overridden by the person submitting the batch to TrailMask. And also trail search parameters, so that, for example, you may say that you don't want to consider any trails that are narrower than a certain number of pixels, or maybe you only want to analyze a certain part of the image, all of which, of course, reduce the processing time. And these last two here can often be found in the image header or deduced from the image header information. So this would be a simple mode of doing this, where literally you do it, and it's doing a fairly mechanical process, and it may well just use something called the Huff transform, which you can look up on Wikipedia, and there are also some very good YouTube videos. Basically, what it means is that you have, if you consider each pixel in your image, there's a very large number of lines that could be drawn through each pixel in your image. So if instead of considering those pixels in the XY coordinate system on your image, you think of the classic y equals mx plus c formula for a straight line, what you do instead is you consider these points plotted as lines in the gradient intersect graph. And when you get a lot of pixels that form a line, as in a trail, then you will see a cluster of intersections of lines in the gradient intersect graph, which will identify the gradient and the intersect of that streak. So it sounds more complicated than it actually is, but computationally it can be quite heavy, depending on how big your images are and how many streaks there are across it. But apart from the simple mode, there's also a move to use deep learning. So effectively to train AI software on images that are submitted to it, where you provide an image that doesn't have any streaks, and you provide an image that has the streaks in it, and you train the software to recognize the streaks and how to process them. And there are some very generic teachings that can be done with the AI that will apply fairly broadly across a lot of circumstances, but it may be also that a particular observatory may want to add their own specific additional training to the AI so that it can process their images more effectively than just the general learning that the software has done. And it may also be possible, if you've got trails across your image, it may also be possible to use some of the results from PassPredict to say, there's a streak here, I don't know what it is, but maybe PassPredict will say, well, there's a streak that passes within a couple of seconds of arc of where that one is, and therefore very likely they are the same one. So all of that can also feed into TrailMask to try and post-process your images. So that was meant to be a very quick rundown of what the software that's being developed as a result of SATCOM1 and SATCOM2 is leading to. Okay, thanks very much. Okay, so we have now a Q&A, so we can start that a little earlier, a couple of minutes early. Would we perhaps start off with the question that Gary asks? So Gary Hunt asked, thank you for a very informative presentation, Jeremy. I note that you mentioned that SpaceX will now dispense with the visors so that laser intercommunication can take place. Do you know what Starlinks will be used to replace, if anything, the visors? Does this mean that subsequent launches will be brighter? And also he then asks a corollary question, will this mean an increase in specular reflections from Starlink?
Okay, thank you very much. That is a good question. As far as I'm aware, with talking with my colleague, Jonathan McDowell at Harvard, we don't think they're using anything to replace them. So basically, they're going to be like they were at the beginning. In terms of making them brighter after launches, technically, once they're on station, yes, in theory, they should be brighter. So now back down to magnitude 4.55s. However, when just after launch, Starlink, after communicating with the astronomy community, had basically changed the cross-section of the satellite in terms of its position towards the sun, so they appear more knife edge. So that reduces the amount of surface area reflecting the light and therefore reduces the brightness. So in theory, without the visors or with visors, they should still be roughly the same brightness at that stage. In terms of specular reflection, that's basically when the light is reflected off the solar panels, and it's basically for a brief period of time, called glints and micro glints. Potentially, Starlink are trying to arrange those solar panels so that way the specular reflections are reflected back into space, and so they aren't visible from the Earth. So even without the visors, the number of specular reflections should stay the same, in theory, hopefully. I hope that answers your question.
Okay, thanks. Andy, you had a comment?
Yeah, this could be a question either for Jeremy or Paul. I believe that the operators and US Space Command have ephemerides that are more accurate than are released as the TLEs. And the TLEs are typically truncated for security purposes, so you can't shoot things down, basically. I have a memory, but I'm not quite sure I've got this right, that at SATCOM2 there was some discussion of whether the operators could release more accurate ephemerides privately to something like the new CPS in order to provide more accurate predictions, but without so that can give so you can have more accurate positions in the sky without necessarily giving a more accurate three-dimensional position for naughty people to shoot things. Is that a real prospect, and do we know if that's actually under discussion? Oh, and by the way, part of the point there is that because the US Space Command have this information, it doesn't necessarily rely on the operator's playing ball, although they might be upset.
Yes. I suppose, I mean, I don't know the answer to the question, but I suppose the thing too is the operators tend to have a fairly good idea of where their satellites are, where they're supposed to be. Yes.
Well, so some
Olivier?
discussions we had with the Starlink people, they did not tell us the precision at which they know the position of their satellite, but they were saying it is orders of magnitude better than what we need, which makes sense, and that they would be happy to share a degraded version of that is better than the TLE with observatories. So basically, they were saying that from the technical point of view, it's not a problem, and they were confident that their legal department would find something. So it's not a technical issue; it's a matter of finding the right terms to receive these, possibly with non-disclosure agreements or further degradation. But so the information is there, and we, the astronomer, could get it. That's for Starlink. Typically, OneWeb follows, they tend to agree to about the same things. But of course, these are the operators we know. Then there are all those with whom we do not have contact yet, and some of them might not play along. That in that case, we rely only on the external measurements. But so bottom line, yes, we need better TLEs, possibly even better format.
Yes. I suppose as time goes on, the tracking is going to have to get better as LEO gets more and more crowded, and you're going to need to take avoidance maneuvers. You need to know the position of your craft to a better degree of precision, so that you don't avoid one and blunder into the path of another. So it may be that as time goes on and as tracking becomes more demanded, then maybe positions will get better anyway.
There are also some private companies who start to collect that data, that type of data, to sell it across operators. And so the question is, could we buy that data or have access to that data for the astronomical community? So I think once the data are there, we'll find a way to get access to it one way or another, either through goodwill or through purchasing them.
Yes, and again, of course, the precision of it that they produce, that they have, may be higher than we need. And so in the same way that, for example, with GPS,
exactly,
most people have GPS at a reduced precision compared to the military use of it. So the same would apply. We would get a sufficiently degraded, but not too badly degraded data from them.
A related thing that I wanted to ask is thinking about the projection into the future and Paul's hurricane comparison. I mean, that's to do with dissipation, basically. And is the friction at 500 kilometers strong enough that actually projection into the future is less certain than it is at 1200 kilometers? So is it in fact easier? You know, maybe Jeremy, for instance, you know, do you know whether the TLE accuracy is better for OneWeb than it is for Starlink, for instance?
Yes, the TLE is generally slightly better. With the supplemental TLEs that we're using, it's done through Celestrac, and they use the GP4 atmospheric modeling stuff to predict atmospheric drag. And that's basically due to space weather. So when you're having a large solar activity, increases the atmosphere temperature of the atmosphere, increases the scale height, increases the density, increases atmospheric drag. And I think that something like that happened to a batch of Starlinks. Like 30 of them didn't actually get into orbit because of the extra drag coefficient caused on them. But we have found in general that the OneWebs are slightly more accurate, yes.
Okay, thanks.
Any more questions from people? Any more comments from the panelists? Olivier?
Yeah, maybe to go back a little to the issue of the VisorSat, and what I'm about to say is really just based on what we heard yesterday from David Goldstein. Indeed, they are going to retire the visor, but he mentioned nadir specular surfaces, so basically to have the bottom of the satellite polished, and that would indeed increase the specular reflection, but it has the potential to dramatically reduce the brightness of the satellites outside of these reflections. So that might, again, it's based on what he said yesterday. So I don't know if he's still, I don't see him around. If that works, that means that it would be for general purposes much better than visor. And then we have to deal with the specular reflections. However, first, they are extremely localized. In the era of the iridium reflections, that a flash was affecting a band of a few tens of kilometers on Earth, and so that means it's really small. And outside of that band, you're not affected at all. And the other thing is that these specular reflections are very well predictable. So that means that if the price to pay to have satellites that are 1 or 2 magnitude fainter is that we have to get a small number of flares, I would sign for that immediately. I had run in our 2020 paper, I had run a calculation for the effect of specular reflection, so flares like iridium, and while they are spectacular, they are so short and so localized that for astronomical observation, the chance to get your telescope at the right place or at the wrong place at the wrong time is extremely small. So that would really help. Also, but that goes back to discussions we had early 2020 with the Starlink people. What they were saying is that they control the attitude of their satellite in real time. And so for them, it would be feasible to wobble the satellite so that the flares don't go on big observatories. So basically, they would have a list of observatories and make sure that the flares goes around the observatory. But okay, these were informal discussions with the engineers 2 years ago. So technically, that's something that they could do and that the engineers would consider feasible. Then, of course, we need to see if that's viable in terms of their operations.
Yes, I had some talk yesterday about dielectric mirrors. Can you remember what the context of that was on the satellites? This was David Goldstein, I think, when he was talking.
I don't know more.
You don't recollect that. I have a question here, another question from Gary Hunt. Olivier mentions companies that will send orbital data. Are you referring to Leo Labs, for example?
I think it's one of them, but there are various companies. Okay, the way I see these is that they tend to contact the observatory to see if we are interested. And our reply typically is, no, we are not directly interested ourselves, but contact the IAU center.
Right, yes.
I think this is part of the plan for Privateer as well, the company that's been started by Steve Wozniak and Moribud Jar. And I think their plan is to release on medium to long timescales to have that free from their website, but for rapid timescales to have a service that you can pay for. So I think that's their business plan.
it's all part of the commercialization of data, really, isn't it?
It makes sense. I mean, there is the same for weather forecast. If you want super accurate weather forecast, you pay. If you are happy with the generic weather forecast, you get it for free. So
yes.
By the way, it's a shame that we haven't got Federico here. I mean, he gave a nice talk, but I mean, some of this, the business of trying to make the glints of the specular reflections avoid particular observatories, that reminds me of the discussions that were happening for radio observatories. That it, you know, obviously because the side lobe collisions are very hard to control. You're going to suffer for them all the time. So the only solution essentially is to I think is to switch off when you're flying over major radio telescopes, which is still annoys. I mean, there isn't too much amateur radio astronomy, but luckily, but there is some, so they
yes.
maybe have a really bad time.
Although their antenna receiver system is going to be probably less sensitive than the professional ones.
Yeah, I think they'll still have a problem though. I think they don't know too much.
Yes. One of the questions I wanted to ask Federico is that we know that there are protected bands in the frequency spectrum for radio astronomy. But of course, as we know, many of the objects that are being observed may have a decent redshift, which means that the emissions that you're interested in are shifted out of the protected band. And presumably that's a problem for the radio community.
It is, and it's partly redshift, but also radio astronomy these days tends to use wideband receivers for sensitivity reasons as well. But also historically, they've kind of fallen into a long-term historical trap because having wideband receivers is developed long after the creation of those protected bands. But people haven't worried too much because they've concentrated on geographical protected zones instead. But now that suddenly becomes irrelevant unless you switch off the satellites as they fly over. But I think they've commerce is catching up with them. But also it's to do with the as Federico said, the scattered electromagnetic radiation and the sideband leakage from cheap electronics and so on. And that's yet another thing that could be, even if Starlink and OneWeb sort of work with radio astronomers and are very careful, you have no idea what other operators in the future are going to do. So that's a very difficult problem.
Yes. I mean, I say the other thing that concerns me is the interest that's being shown in several quarters, including in the European Space Agency, for progressing power from space, where you have very large reflector systems up in orbit to gather solar energy and produce a microwave beam that will be beamed down to Earth. And they're looking at these really very large. I mean, I saw somebody talking about a system of a 2 kilometer wide set of reflectors that would gather light, and this was a serious proposal that was being considered. If you had want some of those up there, then that's really going to affect the night sky. I think Starlink would become the least of our worries. Okay, any other comments before we...
Good news about these projects is that the down beam of the microwave causes so many problems that
Yes.
I suspect that the astronomers will be the least of their problems. And I mean, it goes like flying migratory birds who are flying through the beams. And so there are really some very interesting questions.
Yes, you'd have to have some no-fly regions for aircraft, and also, of course, you have to know what the impact of the beam on satellites in lower orbits would be as they passed underneath and passed through the beam. So I think, yes, there are some interesting questions there. Okay, if there are no more questions, then what I will do is we'll go into the break, and we return at 20 to 4 BST for Connie Walker's talk. And I see Connie's here. Hi, Connie.
Hello.
Hi there. So we'll take a break now and come see you later. Okay, thank you everyone. This is now the last session of our webinar, and I'm very pleased to be able to invite Connie Walker to give us a talk and tell us about the new IAU CPS organization that's been set up. Over to you, Connie.
Thank you, Paul, and thank you so much for allowing me to present today. I'm honored to be here in front of such illustrious speakers. Thank you so much. Today, I'd like to talk a little bit about sharing the sky, the IAU Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference. That's a long title, so we have elected to shorten it to IAU CPS. So you'll hear me interchangeably saying IAU CPS and IAU Center, and that's what I mean. And I'm not alone in this. There's a lot of people involved, but just right now to introduce the management team. Besides myself, we have Piero Benvenuti, who's the director of this entire center, and Federico di Vruno, who's the co-director along with myself. So I'd just like to provide you with a short introduction or outline of the talk. And we're going to go into a little bit of the IAU, and the IAU stands for the International Astronomical Union, and most of you are astronomers and know that, but for those of you who aren't, that's what it stands for. And then a little bit more about the IAU Center and the foundations of what it took to create the IAU Center, because we basically stand on the shoulders of giants who have come before us. And then a reminder of the main issues. I know you've been all through it, so I'll just glance over that, but just to remind people, in case this is a standalone talk at some point, of the issues that surround satellite constellation impact on our field, and then some organizational information on the center, brief overview of the heart of the center, which are the 4 hubs. I'll go into that, how you can get involved, which after this, hopefully all of you will want to be involved, and a little bit, if we have time, just a couple of the events that are ahead of us. And so the International Center, the International Astronomical Union represents about 12,000 professional astronomers from about 90 different countries, and I think it's actually close to 100 now. The IAU promotes and safeguards astronomy in all its various aspects. And there's 2 lines of action that have been adopted by the IAU for the protection of the dark and quiet skies from satellite constellation interference. And they surround going through the the UN COPOS, the Committee for the Peaceful Use of Outer Space. I have all these acronyms in here, sorry about that. And other kind of organizations such as the ITU, which you've heard a lot about today, and UNESCO, etc. So there's a lot of regulatory guidelines that we can try to address through these different organizations. And also we have feet basically on the ground, which means we're coordinating with community members directly and with stakeholders such as the satellite industry, in efforts to develop and implement mitigation strategies. And this latter action is what the center is basically, what led to the call for the center. And this was something that the IAU put forth, and that both as a partnership, the NOIR Lab, which is a funny acronym for the actual National Observatory of the United States, the Optical Observatory, Optical Astronomy Observatory, and then also the Square Kilometre Array, headquartered in the UK. And this partnership and this proposal was accepted by the IAU, and the center opened just a month ago. So, and its mission is to basically coordinate efforts and endeavor to unify voices within the global astronomy community, primarily. And it's also to bring together different stakeholders like the astronomers and industry and the wider community, which includes people like space lawyers, which we've had involved with our different workshops I'll tell you about in a second, and indigenous communities and communities that are not really astronomy oriented whatsoever, but should have a voice in all of the decisions that are made. So this is something else we're trying to do, as well as produce and disseminate information and various resources to which any stakeholder group can contribute, and also from which they can draw in support of their own activities. So, so it serves various purposes. And the hubs that you'll hear about in a second, the various areas of the center, will continue research in the various satellite constellation issues to hopefully arrive at feasible and implementable solutions in the various areas of observation and software and national and international policy, industry and technology, and community engagement. So let's see. Oh, it's stuck. There you go. So some of the foundations, as I mentioned before, we stand on the shoulders of giants, and this is we didn't kind of create all this out of the blue. About a year or less after the launch of the Starlink satellites, which kind of shook up the astronomy field and very surprised a lot of us. We actually started a series of 4 different workshops, and many, I'd say more than half the people who are presented here have been involved in these workshops and really set the foundation for everything that came after, i.e. the center. So the 4 workshops for the first 2, called Satellite Constellation 1 or SATCON 1 and Dark and Quiet Skies 1, actually identified the issues and formulated and recommended some of the mitigation strategies. And in the SATCON 2 and Dark and Quiet Skies 2, they're basically the sequels to the first ones. They identified the paths to implement the recommendations. And then they actually, and now we have the opportunity through the center to take the pathways to implement the recommendations and these solutions. So that's our history, basically, for all of the information that we have so far with respect to the implementing solutions to satellite constellations. And we've been working with industry just to make that point, and we've been involved with, as I said before, the UN and the various meetings that we've attended for the Science and Technology Subcommittee, for instance, which is part of the Committee for the Peaceful Use of Outer Space. So there's various things that we're doing. It's like a multi-pronged fork, basically, with different avenues that you can take. But just to give a superbly brief overview, I just want to remind people that a lot of the big issues, some of the big issues surround the numbers of active satellites and also the inactive satellites. And so we have the really big thing to note is that it's been 65 years basically since the launch of the very, very first satellite. And it's was all the way up until 2019, before the launch of the Starlink satellites, that we only had maybe 2,200 active satellites in the sky. And after that point, we it rose quite steeply and quite quickly to over 5,000. I'd say it's probably over 5,500 active satellites at the moment, and then a few more thousand that are inactive. And then we have these the space junk that's up there, and only about 42,000 of the space junk that's up there is trackable. So that's kind of a sobering thought. There's a lot of things that are not trackable. And many of this, they have to be basically bigger than 10 centimeters, and smaller than that, you have, some people have a conservative estimate of 600,000 that are between 1 and 10 centimeters, and some people say 1 million. So there's a lot of things to contend with and all the problems that provides. I'm trying to get this to work. Here we go. And then there's the other kinds of risks that the satellite constellations impose, such as not only the number that we talked about, but the brightness and the fact that we have no regulations with respect to optical astronomy thus far. We do have, as you've heard, a good establishment of some limited protections for radio, but not really for the optical yet, and that's a problem before us. And then there's also the diffuse sky brightening that's happening because of the aggregate of all these very small, basically space junk up there, and that is contributing to the increase in our background light pollution, basically. So we have a lot of things to contend with here. Very slow response here. I'm sorry about that. And then turning to radio astronomy, you have constellations with high power radar that can potentially damage sensitive equipment on radio telescopes if directly illuminated. You've heard a lot about that today, I think. Constellations can affect protected radio wavelength bands, and they can also affect wideband receivers that can see many different wavelengths at once, to put it simply, and then they can obviate radio quiet zones when they fly overhead. So that's just a summary. But also, it's not just the fact that they're physically impacting the observatories, it's the science that's really, really impacted. And just to touch base on that, to continue with the radio astronomy theme here, there's cosmic microwave background studies. They require high sensitivity due to the very faint signals they have to detect. And they're going to be very highly impacted by the satellite downlinks, as well as other studies like molecular gas emissions that are redshifted into the satellite downlink frequencies, and also high mass star formation, which again does require molecular gas studies, but it's very particular to wavelengths that are congruous with the various satellite downlinks, like 12.2 gigahertz for the masers that they kind of they want to study. So for optical astronomy, it's one of the high important, very, very important studies is the potentially hazardous asteroid missions, which the IAU is involved with. They have a global network that many countries many different observatories are involved in, and these will have fewer discoveries and orbit determinations of potentially hazardous asteroids, if with the impact of the satellite constellations, and any science that require observatories that have wide fields of view and sensitive detectors that require that type of equipment will be severely impacted. So you have these studies from the telescope like the Rubin Observatory coming online that are going to take a 10-year movie of everything that goes bump in the night, as they say, or a variable astronomy that require high sensitivity that will be severely impacted as well. Okay, so and so just to get into the guts of the center a little bit and to show you our humble organizational chart here, we have the management team, which I've already introduced to Piero Benvenuti as director, and Federico di Vruno on the right-hand side here as co-director from the SKAO, and myself as well. And we constitute the management team. We report to the IAU Executive Committee from time, once every great while, and also the governance board, which is made up of people, leadership from the Noir Lab and from SKO and from the IAU. We have an advisory board that we're forming at the moment. We have 10 wonderful candidates we're going to be inviting, and hopefully they say yes. And we have the 4 hubs. I'm going to go into a little bit more detail, not too much, but about SAT Hub, the Policy Hub, the Industry and Technology Hub, and the Community Engagement Hub. And these will be have members from what we call the contributing members and the affiliated members, and I will go into details about what they constitute as well. And just to show you, we've been a tiny bit busy in the last month or so trying to set things up. We already have our logo, as you can see here. We had a great time trying to figure that one out. We are almost ready to launch our website. We have a master work plan in action. Well, it's almost done. And a communications and strategy and plan, as well as a financial plan and account and questionnaires that we have almost ready for our potential members, as well as a membership agreement. We're going to be announcing that soon. And we're, as I said before, forming our advisory committee. So we're not slouching at all. We're having a good time planning all these things for the benefit, hopefully, of our community. And then this is the details a little bit about the 4 hubs itself. We have leading the SAT hub, which I'll mention in a moment what that is Meredith Rawls. She's been long at this during SatCon 2 especially, leading the group there, and in Dark Quiet Skies 2, a related group that basically created SatHub, the idea of SatHub. And we have Richard Green and Andy Williams. Richard is from the University of Arizona, and Andy is from ESO. And I meant to say that Meredith Rawls is associated with the Rubin Observatory and is from the University of Washington. And Richard and Andy are leading the Policy Hub, and John Barentine, whom you heard from earlier, and Jessica Heim, who you also heard from earlier, is leading the Community Engagement Hub. And then for industry, we have Chris Hoffer, who has led both industry groups in the SatCon 2 and Dark and Quiet Skies 2. And he's from Amazon Kuiper. And Tim Stevenson is from the Square Kilometer Array Observatory. And they're co-leading that particular hub. Okay. So just to give a tiny bit of detail of each of the hubs so you know what they're doing. In SatHub, we're trying to create an observations network to look at these different satellites and see how they affect data. We're going to create an astronomical repository for that data. And that most importantly, we just submitted, I'm very happy to say, a proposal to the National Science Foundation for one of the software tools that will be part of SatHub, and that's to predict the passes of the satellites. And then we're going to have other kinds of software, and we have quite a few ideas, but one is that masks trails. So it's just to give you an idea. And then we want to have training curricula around this so that people can actually be able to use these different tools we're going to be offering, and lots of real-time collaboration. The Policy Hub is basically going to be a portal of existing national and international policies and regulations. And they're going to have a policy forum for interested national policy makers and stakeholders, and they have already started to coordinate actions among COPUS, or Committee for Peaceful Use of Outer Space, and part of the UN, delegates and observers. And then they're going to basically also study and compare ITU-R, which is the radio portion of the International Telecommunications Union, their regulations, because they're very well established, and see how they could be extended to the optical infrared cases. Okay, very slow here. There we go. So the Community Engagement Hub, they're going to be identifying communities that want to get involved. We already know quite a few because they had previous experiences in the last 2 workshops. But they're also going to basically use the satellite constellations as a case study, and have very, very fair-minded discussions, as they have already, on technical development versus human progress, and give the people, try to understand the duty to consult the different communities, basically, and then collaborate with the IU offices, which include the Office for Outreach, Development, and Education. And then for the last hub here, the Industry and Technology Hub, we want to do various things, but mainly to develop standard measures of mitigation strategies or successes. And they've already built basically just a draft, though, of best practices of mitigations and guidelines, what the astronomy community and industry can do together to implement some of these mitigation strategies. And they also want to be involved with the outreach and for stakeholders in the public, and to create various tools and education materials for the stakeholders and public as well. So lots of good things involved here. Okay, so for the just a little more on the industry hub, this is, I think, when I thought of the title "Sharing the Sky," it really is a matter of getting to know the different cultures and the perspectives of the different cultures and what can be done, because no one's going to get everything they want, unfortunately, when it comes to this the issue of satellite constellations. So we have to work together and share the sky. And in terms of the technology hub, this is going to be pretty strategic to try to keep the sky, keep the individual satellites as dark as possible, basically, reduce the visibility of the satellites, provide high accuracy public data on the satellite locations, directly, well, avoid directly illuminating radio observatories, for instance, and complying with the what they call the ITU equivalent power flux density limits, which have to do basically with the measure of the strength of the radiation in the far field. So let's see, those are some of the main points that they're going to be looking at. So there's two groups of memberships that I mentioned before. One's contributing members and the other's affiliated members. The contributing members are the ones that are really involved and are going to have the opportunity to work very actively with us and become members of the hub and have access to the resources. And we hope that they have a commitment to what kind of resources they might be able to supply, and they get a chance to develop their own work plan to tell us how they would integrate with the center. The affiliated members basically contribute on a best effort basis. We don't want to exclude anybody that would like to be a part of the center and contribute. So those two are the varying degrees of how to be involved. And some of the areas that you can get involved in, this is not exclusive, this is just suggestions, but we would like people that would help with the observations and help with the various industry interactions. And also we have this keen interest from the industry to develop hardware mitigation strategies, like with the BRDF, brightness basically testing in labs. So that's an area. And then partnering in the various software that has to be developed, regulations development through either COPUS or nationally within countries, and interacting, as I said before, with the various IAU offices, and helping us with our website, because it's going to, I think it's going to become rather large after a while. And we're going to have hopefully thematic workshops, and we'd like help with that, and various discussion forums, because we really want to hear everybody's opinions and try to implement them as best as possible. And then also curriculum development, which I mentioned before, and various outreach efforts. And we're going to have a membership form that's going to be available in the near future. And we're hoping that you'll fill out one of these either on your behalf or on your institution's behalf. And in all these areas that I mentioned before are going to be some of the choices that you can get involved with. And we just want to know things like hours and how many people might be involved. And various events ahead. We have I don't know, half a dozen that are ahead in the near future. One that's with the Office of Astronomy for Development and the International Day of Light on May 16th. We have a presentation there. There's a Dark Skies Awareness Month this month, if you're not aware of that. And the Office of Astronomy Outreach is having us talk on the last day of the month. We have a splitter session we're organizing for the American Astronomical Society on June 13th in the afternoon. And that's West Coast time in the United States. And the Secure World Foundation is having a summit on space sustainability, and we're making a presentation there as well. And that's the third week of June or so. And the IAU, very importantly, we're having a 2-day conference. One of the 2 days is dedicated to satellite constellation interference on August 9th. And if you want to know more about that, there's the website for that. You can find it too underneath the IAU website. And that's about it for me, guys. And I thank you so much for bearing with me. And this is our contact information for both myself, Piero, and Federico. And we have some temporary websites. They're not the final ones. So thank you so much.
Thank you, Connie. And in fact, Piero has said that he's happy to join our Q&A panel later on as well. So that's good. Him being here, I couldn't let the opportunity pass to ask him.
I'm very glad to hear that.
Now we have a few minutes spare. Does anyone have a question, or any of the panelists have a question they'd like to put to Connie?
Maybe I was either too quick or too thorough.
I was looking for a hand going up or something like that, but I have no questions.
Well, maybe just one comment to give time to the others to make up real questions. Connie, it's really great to see that the IAU Center went from not even being thought about to becoming a reality in 2 years. And we have made, I mean, the community as a whole has made so much progress through the 4 big conferences plus all the mini workshops here and there. And I think it's really amazing how all these efforts are coming together and pushing in the right direction to discuss, to find solution, to try to pragmatically find solution that work best for everybody. That's really amazing. And for all the audience, Connie was deeply involved from the beginning in all these conferences and all these workshops. So I think it would not have happened without you. Thank you, Connie.
Well, thank you very much for saying that, but it's really everybody that was involved, and I counted about at least 150 people who were involved in all those 4 workshops in terms of satellite constellation impacts and addressing the issues and mitigation solutions. And I have to thank them, and especially you, Olivier. I forgot to mention that on one of the slides, I had your GIF operating, and it's a beautiful GIF, and I know it's not probably one of the latest ones, but it's an incredible visualization of the visibility of satellites. I mean, actually being able to see them. They were the ones that were in yellow during the nighttime. And thank you so much, Olivier, for all your research. Andy, I see you have your hand up.
I do, yes. I just wondered actually whether the center will but whether it will mostly coordinate existing activities and working groups, etc. The contributing members, etc., or whether there are plans to for the center to have its own budget and hire new staff. And if so, how are you going to do that?
Yes, we are going to be a little bit of both. We're going to be a coordinating center mainly, but we are hiring staff as soon as we can get some other. Well, for instance, the National Science Foundation from the U.S. We have a budget in for 3.5 staff members, and the half of that is me. But there's hopefully going to be money for that if they approve of that. We just put in a budget for a postdoc and to do the programming for one of the PassPredict, we're calling it, for the Sat Hub, and also part of a software engineer and part of an education curriculum development person. So we are trying to build that aspect of things too. But I think mostly our contributions will come from the contributing members and who hopefully will be also members of our various hubs and their working groups. And I think Piero wants to say more. Piero?
No, I think you made perfectly correctly the scenario that we are working on. So we will not have a big staff working for this center directly, but we know that we can count on a excellent collaboration with the community, which we saw already in the preparation of the conferences and the workshops, the SATCON 1 and 2, and the 2 conferences. And also, when we organize, before starting the center, the so-called listening sessions, inviting everybody who's interested to join and listen what we want to do, and asking if they were ready to collaborate with us. We had a fantastic response. Almost 180 people responded to the questionnaire, and a good fraction was saying that they want to become a member, either collaborating member or affiliated member. We are now ready to send around another questionnaire more specific, which is a way to define better who can be collaborating with us. And we have ready now the kind of agreement or form, to establish the proper set of the collaboration. And we are creating a database with all collaborations. So essentially the main task of the center is to coordinate this effort and to accept all the collaboration that we can see around. If I may, there is one point that I think is worth mentioning in this. First of all, I mean, congratulations for organizing this excellent national and international webinar. As you see, we try to move very fast on this center and this coordination and achieve mitigating measures that can be immediately applied to astronomy observations. However, the IAU is not forgetting the policy part and is quite active in promoting the case of the protection of the sky at the level of the UN Committee for the Pacific Use of Outer Space, for the peaceful use of outer space. And we presented our case together with a number of delegations at the last Scientific and Technical Subcommittee in February. And we had 25 delegations intervening in support of our effort and expressing concern about the impact of the constellation on astronomy and science in general. 25 is a quarter of the total participant in the forum of the UN OOSA, the Office of Outer Space, or the Committee of the Peaceful Use of Outer Space. So it is a significant fraction of the nations that are now being aware of the problem, and we will rediscuss the issue next year at the following committee meeting of the Scientific and Technical Subcommittee. We know that we already have a dedicated agenda point for this, so we will review the situation at that point, and we'll see if our approach, which is essentially a collaboration with industry and companies to find the best mitigating measures, is working. And we hope that in this way we can catch up all with the incoming companies that we will deploy other constellation. I mean, the danger so far, I mean, the collaboration with existing companies has been quite good, but the danger is that we have other companies coming into play and deploying large constellation without any preoccupation about the impact. And so by raising the attention at that level, we hope that we can control the situation in a suitable way. And we will report back also at the real COPUS committee in June, just informing of the starting of the operation of the center, so that the delegation will know that what we are doing, and we will continue to be present there. And I think astronomy has never been so visible at the level of the UN committee. So some success has already been achieved with the effort and with the help of all the community that has been giving us a lot of support.
If I could just follow on slightly from the budget question, sorry to harp on about this. If it's possible, it could be quite nice to estimate all the in-kind effort as well as anything direct that's been caused to cope with this problem. I think, as you know, as part of the environmental approach, we've been making a fuss about externalization of costs or displacement of costs. And it might be nice to have a kind of ballpark number that we can use in various public circumstances.
Yes, absolutely. In fact, we plan to do that, and also we want to, once we have identified the mitigating solution that we want to offer to the entire community, we will have to estimate the cost of implementing that, because I mean, one thing is to develop a prototype and offer that at the academic level, but if we want to provide a service like being able to predict precisely the incoming of the satellite in the field of view and providing that as a service open to anybody, that is it has a cost, and we want to estimate that, and then we will start a fundraising campaign with that. But I mean, that will show what is the financial impact, if you like, of the constellation on science, and so that will certainly be used publicly in such a way that people understand what is the impact on investment. That in general, I mean, we have an investment in research that is developing facilities, large facilities, and operate large facilities. Now they are being affected by this situation. So we have to explicitly say how much it is. So absolutely, we will do that.
Very good. And I'd assume that would include, repeating SKA observations or whatever, right? I mean, they're still taxpayers' pounds and dollars.
Yep. Yes, absolutely.
Okay. Thank you very much, Pierre. Thank you for the contributors there, and thank you, Connie, for your talk. Perhaps we could move on to Jeremy's second talk, and then we have the final talk from Juliana, and we have a Q&A session at the end. Thank you very much. So on to you, Jeremy.
Thank you. Okay, hopefully I can share my screen this time without any issues, because I've learned. Okay, and then slideshow. There you go. Can you all see my screen okay? Is it full screen?
Not quite yet. It still says screen sharing. I think there's a little bit of lag between you and us. Yes, now I've got full screen. Yes, there you are.
Yes. Excellent. Yeah, I do apologise for that. It's I'm doing these talks from home, and we don't have fibre internet, so I'm using 4G cellular internet. Which, yeah. Okay, so thank you again. Basically, that was really lovely talk there by Connie just now. I'm going to be touching on part of this regarding the Central Repository of Satellite Observations, both with a bit of work that Meredith is doing with SatHub, and also a bit of work that we're doing with CleoSat, and hopefully explain the sort of observations we're doing to characterize the satellite brightnesses and characterize the TLE accuracy, and how these observations can be used, and so therefore what sort of observations would be most beneficial to us. I do apologize. I'll try to make my two talks completely self-contained, so there will be some slides in this talk that I showed in my previous talk. The idea is that each talk's its own self-contained talk. So quickly, just a bit about me, for those who didn't see my first talk. I did my undergraduate at Lancaster University. I then did my PhD at Keele down in Staffordshire. And then after that, I did a 2-year postdoc program under a NASA postdoctoral program fellowship at NASA Ames in San Francisco Bay. And then after that, I did a Fondesit postdoc at the Universidad de Antofagasta. And then about a year ago, I basically started my first faculty position at the Universidad de Atacama. So a little bit about SatHub. Basically, the whole idea is to become a one-stop shop for training, outreach, and data collection analysis of satellite observations. I'm mainly going to be talking about the astronomical data repositories and visual records and astrophotography and all the sort of data that we need that will help researchers and people throughout the world connected with SatHub to be able to do these analysis, test their codes, test their models, test their predictions, and forecasting software, and to basically aid on an international community level to allow us to help try and mitigate the impacts of these satellites to astronomy. So mainly for the astronomical data repositories, we need them to be publicly and easily accessible. They need to be user-friendly and documented, i.e., it's all well and good having them in some sort of pickle files, which only can be accessed using R or Python, but we need to make sure that they're easily accessible and anyone can just log into the website, say what observations they're after, and just be able to download them all. The idea is to form a collection of both optical and near-infrared images with satellite streaks, also potentially any spectra contaminated with reflected solar spectrum. Also space-based observations from low Earth orbit, e.g. the Hubble Space Telescope, because it's around about 400 kilometers. Some of these satellites do pass over the Hubble Space Telescope, and so some of the images from Hubble has been affected. So that kind of mutes the point when people turn around and say, well, just launch more space telescopes. Well, we need to have them in higher orbits then, which, like if you have with the JWST at Lagrange 2, means it's not possible to service them. So once they expire, they've expired. Also, we want to be able to have radio data impacted by satellite interference in there for people working in the radio mitigation section. And also, we want to collect all types of formats, DSLR images, visual sightings, and various other formats. So, okay, we'll now take it back to the first stages is, okay, I want to go and make some observations. Let's collect some data so I can then upload them to one of these potential repositories. So first of all, what we tend to do is we download the latest TLE data from Celestrak. We normally download the supplemental TLEs. And if you open the files, you get this lovely, compact information, which, it's a bit difficult to read, and it's a bit like, okay, what's going on here? So what you then do is you then run a orbital model or orbital equations model to extract that in terms of ephemerids. And from that, you could then, just like you do with software to determine the position of the sun and stars on the night sky with sidereal time and location on the Earth, you then can run it through a code to then get basically the times and positions of where to observe these satellites. For example, here, we've got Starlink 1945, we've got the date back in December, 12 UT, and it gives you the REM declination to make the observations. Here, these are all negative because we're in the Southern Hemisphere, so most of our observations are 10 degrees southwards, lower. So, okay, we've got our positions. We point our telescope to the patch of sky that we want to observe the satellite. We generally use the wait and catch technique, where basically we say, okay, we know where the satellite's going to be roughly at these coordinates. We point our telescope there a minute or so before then, and then we begin the exposure roughly. If we're doing a 10-second exposure, you then normally set the exposure 5 seconds before the satellite's due. So hopefully the satellite passes through in the middle of the exposure time. And the reason we do slightly longer exposures is because basically we want to measure the magnitude, the brightness of the satellite. And to do that, we need to get a good signal to noise ratio for our comparison stars in the image. We then also afterwards do a second observation without the satellite streak that allows us to get an unaffected image. This is for 2 reasons. First of all, we've got identical patch of sky, one with a satellite trail, one without a satellite trail, to feed into any potential future machine learning algorithms to detect streaks. Also, and this is more importantly for the work that we do, is that sometimes you get a satellite trail passing through a star. And so if you're calculating the brightness of that satellite streak and there's a star in there, it's contaminating it and can skew your numbers. So basically we want a satellite streak-free image so we can work out which stars the satellite streak passed over, characterize the stars' stellar PSF, and then we can then remove it from the satellite trail. And so therefore, when we actually calculate the magnitude, the brightness of the satellite trail, we're actually only doing the satellite, not any stars it's passing over. So as you can see, these are some of the observations we got of, I showed these in my previous talk, of some Starlink satellites and OneWebs using our telemetry code. And generally, they're quite well spot on. We're actually normally getting quite well. Obviously, every now and again, you take an image and there is no satellite trail at all. And basically, we just assign that to the simple fact that there was an on-station maneuver or avoidance maneuver. And so the telemetry of the satellite is completely different to what the TLE says. And the only way you'll pick that up again is when the new TLE is created published 8 hours after the first one. Okay. Oh, I'm still there.
We're still here.
Yes, we can still see you, yes.
Okay, sorry, my laptop said poor connection, sorry. Okay, so when we get our image of the satellite streak and we want to calculate the brightness, what we do is we do, just like we do with aperture photometry, we basically want to count the number of the pixel counts in the apertures of both of the satellite's trail, but also of the comparison stars in the image. And so basically going to Photometry 101, we create 3 apertures around our comparison stars, where basically the inner aperture is for the target, and then the outer 2 apertures allows us to calculate the average sky background, because the sky has also got is providing a light source. So we need to remove that from our source pixels. So we only actually calculate the actual flux from the actual target. And so once we calculated the average background pixel noise, we then subtract that from the average value from all the pixels within the inner aperture, and then we then integrate the flux. Basically, we count up all the numbers inside there. And that then gives us a ADU count or flux count for our comparison star. For satellite streaks, it's a similar thing, but instead of using standard circular apertures, we use box apertures, where basically we have basically 2 apertures for each side of the trail. The inner one where we calculate the flux of the trail, and the outer one we calculate the average background. And basically what we do is we do it in sections, where basically we calculate the average background in this little section, and just deduct it from this section here, and we do the same along the streak. And the reason we do that is because due to different detector responses, some sections of the detector could have a higher readout current, and so basically it could be we can add a few counts into the pixel counts, unintentionally. So basically we do it in sections. Here on the left, we got a cross section of the trail at one of these points, and we can see, even for a 0.6 meter telescope, we're getting a very high ADU count above the background noise. So background noise is around about 0, and so we're close to around 500. And that's just for a 0.6 meter telescope. So once we subtracted the sky background, we then basically integrate the flux of the satellite trail, just like we did for the stars, and basically we get the total flux of the satellite trail. So that then only gives us the partial picture, as I mentioned in the other talk. For example, this image here is a 10-second exposure. So the amount of flux for each of these stars is 10 seconds. However, in this particular image, the satellite took about 0.6 seconds to pass from one edge to the other edge. So basically, we now need to scale the fluxes of our comparison stars accordingly, because the amount of flux in the satellite trail is from 0.6 seconds. So we need to scale everything down accordingly to make sure it's a fair comparison. The other option is to basically scale up the trail length, basically by saying, okay, if this was 0.6 seconds, how long would the trail be for 10-second exposure? But that then also adds additional potential issues. So generally speaking, the best way to scale down the stars. And you basically do this because we know the angular velocity, so we know how long it took for the star to pass from one edge to the other, and say, in this case, it's 0.6, but let's say it's 1 second, then therefore we need to scale the PSF, or fluxes of the integrated fluxes of the stars, comparison stars, to 1/10. Then once we've done that, we can then basically calculate our differential magnitude. Now, when I say differential magnitude, it's basically a difference magnitude. It's the magnitude difference between one target and another target. And we do that for the satellite trail compared to each star. Basically, the difference magnitude is basically the ratio between the satellite and star fluxes. Take the log of it times minus 2.5. Here's a little output for one of the analysis of the previous image. And basically, we have the difference magnitude between the satellite trail and star 1, and that's with the satellite streak as it is. Once we scaled the star's flux, basically we find out that the satellite streak is roughly 4.5 magnitudes brighter than the star. And then using astronomical catalogs such as Gaia or pan-stars, we then can determine what is the magnitude of our star in that passband. Bearing in mind that if there isn't a measurement of the magnitude, we can still calculate it using color equations between different filters. And basically, we can then end up getting the magnitude of the satellite trail. And we do that for all the different comparison stars. So here we've got 4.9, then 5, then 5.4, 5.43. And from that, we can then take these values and we then calculate the weighted mean between them. Obviously, here we can see it's roughly around 5.4 magnitudes, but with one comparison star and a second comparison star, we're getting slightly anomalous values. And basically, what we found was there was a few hot pixels in this contaminating star's PSFs, which altered the calculations. So once we scaled them out, we end up getting similar values to the rest of the comparison stars. So, okay. So now we've got our satellite magnitude. We now know how bright the satellite is. We now need to we now do this for X number of satellites. And basically, we need to do a fair comparison. We need to actually look at the absolute brightness. Now, a bit just like with stars, we have an apparent magnitude and an absolute magnitude. The apparent magnitude is how bright the star is in the night sky, while the absolute magnitude is basically when we scale it to the same conditions, such as 10 parsecs without extinction and dust. And therefore, you can then say exactly how bright is each star compared to each star in its own natural setting. And a similar thing happens to satellites. They've roughly, as if they were a stationary source, they would follow an inverse square law. But as they're moving, I think it was Tony Tyson from the Rubin who calculated it to be about 1 to the power of 1.9 something. So once we scale it, we can do a fair comparison. But an important point to note is compared to geostationary satellites, which have an orbital height of around about 20,000 kilometers, LEO is roughly 40 times closer, and therefore, if it was the same satellite, it would be about 1,600 times brighter. Oh, sorry. Hence, this is one of the reasons why the satellites in LEO are basically more visible to the unaided eye. So, once we scaled to a normalized orbital normalized range, which we normally take as the orbital height. If you're obviously comparing satellites in different orbital heights, it gets a bit more complicated. So you need to select a standard value for this. So for Starlink, we normally do 550 kilometers. For OneWeb, we do 1,200 kilometers. So basically, once we basically take into account the flux follows an inverse square law, we basically calculate, we can then scale the magnitude of the satellite and basically just use the standard log equations of 5 times log r over 550, where r is the range of the satellite in kilometers at the time of the observation, and we're basically scaling it to 550 kilometers. Things then also get a bit more complicated, as I mentioned before. Unlike specular reflections, which is basically a direct reflection, the bodies of these objects are basically a diffuse body, and so therefore they produce diffuse reflections in multiple angles at varying intensities. And so this makes things a bit more complicated as the phase angle between the observer and the satellite changes, the brightness of the satellite changes. And so we need to take this into account. And it's heavily dependent on the properties of the surface involved. So, for example, when we say phase angles, there are 3 types. There's the main phase angle, if I'm using that correctly, which is the actual angle between the incident light and the observed reflective light. And that's basically can be calculated from simply working out the angle between the satellite and the sun in the sky and subtracting that from 180. The other angles, and that angle can therefore be split even further into the solar phase angle and the observer phase angle, where, for example, the observer phase angle is basically the angle between the unit normal of the satellite pointing to the nadir and the observed angle from the observer. And so using some geometry and sine laws, we can basically calculate what the solar phase angle is. However, we calculate the observer phase angle. For the solar phase angle, we need to calculate the position of the sun at the position of the sun relative to where the satellite actually is. So for this, basically what we can do is if we take a simple example of basically that the sun's out to infinity, then basically the solar rays from the sun to the satellite and from the sun to the nadir are basically parallel. And basically what we could do is turn around and say that the solar phase angle is equal to the solar elevation at the nadir point of the satellite. And then quite simply, we can just see here that the 2 angles added together equals 90 degrees. And so basically, we can actually calculate what the solar phase angle is. So the upper image basically shows the 2 angles in relation to the Starlink satellite, where basically the unit normal pointed towards the Earth, or basically the nadir surface of the satellite. Okay, so we can get our angles together, but we still need to take into account the properties of the surface of the reflection. And this is where we basically normally, in optics, we use the bidirectional reflectance distribution function, or BRDF. And this basically takes into account basically the lighting direction, the viewing direction, the half angle vector. We're talking about the microfacet normal distribution function, the Fresnel term, the shadowing term. It gets a bit more complicated. However, to be able to, in labs, how they generally do this, they have the object they want to measure the BRDF, they have a movable lighting source and a movable camera to detect the light, the reflected light, and they move them around at different angles and basically measure the different intensities, and they can then fit the BRDF models to the data. However, sadly, as astronomers, we don't have access to one of these satellites in the labs. And so we have to do this from afar by basically measuring the satellite through our optical telescopes. The problem is we don't actually control the angles. We have to let the satellite move across the night sky and take the images as it moves to then actually ascertain these different positions. So by doing a survey style observing campaign of taking lots of observations of satellites at all these different phase angles, we can then start collecting the data points and then start beginning to fit our models or fit our model parameters to the data and actually try and start begin to understand the BRDF properties of the satellite. However, when we look at when we look at the magnitude brightness of these satellites as a function of angle, so for example, here's with the paper from the Szent-Hetky telescope, we're looking at basically the difference in AZ between the satellite trail and the sun. We can see there's generally quite a large spread in the change in magnitudes, and so basically, while some of this can be modeled can be simply modeled, when we then look at other clusters, we get this nice trend in the data, so we can actually see that the satellites generally get fainter as we change the phase angle from 35 to 75 degrees, but we always get some anomalous results, values that don't actually fit into the trends of the phase angles. And basically, this is what we interpret as basically the satellite's attitude or the orientation. So basically, as the orientation changes, a different section of the surface is being viewed. And so we might be actually viewing different sections of the satellite compared to what we would expect. So this causes a third issue, which needs to be taken into account. And one of the ways that we're doing this is basically trying to look at by performing simultaneous multiband observations in the optical and near infrared. Unlike specular reflections, where everything's reflected nicely, when you've got multi-wavelength light, basically depending on the wavelength, depends on the angle of reflection. And so basically the colors are basically reflected at different angles to each other. So performing observations simultaneously in multiple bands, here on the right-hand side, we've got an example of Starlink 2362 obtained with Grand on the ESO 2.2 meter telescope at the SEA. The four small ones are 5 by 5 arc minutes each, and they're basically the four optical cameras, while the right-hand side is basically the near-infrared J-band camera, which is 10 by 10 arc minutes. But basically what we have here is an image of Starlink 2362 observed simultaneously with each other. In that, in each of these images, we're observing the satellite at the same range, same distance, same phase angles, and same orientation. And so basically, we know that because we're looking at exactly the same thing in all three images, we can then begin to start looking at the color index of the light. So when we talk about the color index, we're talking about B minus B or B minus I. But basically, we're looking, it's what we do with stars, and it allows us to help classify stars. So basically, if you've got a red dwarf star, it will be brighter in the visible, it will be brighter in redder wavelengths. So basically, the B minus V will be a negative number. While if you're looking at an O type or blue star, they'll be brighter in the blue and UV, and therefore you'll have a positive BV number. And so by looking at the color index, we can classify our stars, and we can try and do the same thing with the satellites. In respect that, because we know it's reflected sunlight, we know what the color index should be. So by examining for any divergences in the measured color index compared to that of solar, we can try and start giving us insights onto the different properties of the orientation of the satellites. For example, we can, start modeling the microfacet density using something called a spectrally varying bidirectional reflectance distribution function, or SVBRDF model, similar to the Beckman distribution. And basically what that is basically saying, okay, we've got multiple different BRDF models for different points along the which we're looking at. So that's how we do our work to measure the magnitude brightness of the satellite. So how do we actually measure the TLE accuracy? Again, I apologize for those of you who watched the previous talk. I'm going to be rehashing it all again. But you have two parts. You have the TLE spectral accuracy. And that's basically, in this particular image, the red cross represents the position of where the satellite should have been at the center of the exposure time. And we got the satellite streak. And then you can see the spectral accuracy is quite high. We're looking at about between 1.5 and 0.4 arc minutes. However, unlike stars, which are stationary, the satellite trail is actually it's the function of the satellite's position. It's the position of the satellite as a function of time. So as in this case, it took about just over a second for the satellite to pass through the field of view. Because it's a 10-second exposure, did the satellite pass through 4 seconds earlier? Did it pass through 3 seconds later? Was it in fact here at the beginning on the left-hand side when it should have been at the middle at the correct time? So it's not possible to actually work these things out. So to do this, we use a larger field of view, and also for a shorter exposure time. And here we've got like a 72 by 72 arc-minute field of view, and this is just a 2-second exposure taken with the telescope in South Korea. Here we've got the start and end point of the satellite trail. So at the start of the exposure, the satellite was at one of these points, and at the end of the exposure, it was at the other point. Obviously, looking through the TLE and the orbital ephemeris, we know which direction it's going, plus RA or negative RA, so we can actually determine which point it started at. And then we can integrate the angular velocity of the satellite over the trail length to actually work out the position of the satellite at, as a function of time. And so therefore, when we calculate the position of the satellite, it's supposed to be here at the center of the exposure. We calculate the position actually here at the center of exposure. We can then measure the accuracy of the TLE. And in this case, it's about 18 arc minutes off. Okay, so that's for one satellite. Different satellites undergo through different maneuvers. They're impacted differently by atmospheric drag. And so what we need to do is we need to build up a population so we can study the statistical robustness or the statistical accuracy of the TLE. So this has been done before by Harry. Basically, they did observations, about 560 observations of Starlink satellites, if I remember correctly, with the PROMIS telescope, which is owned and operated by the University of Arizona. And basically, they compared the position of the satellite with compared to the position that predicted by the Celestrac supplemental TLEs and calculated the angular offset. As you can see, most of them are less than 0.1 degrees or less than 6 arc minutes. The observation I showed just now is roughly about 18, so that's about 0.3, and we do get a distributional trail heading off to about half a degree. So basically, there are issues in respect that half a degree is quite large. I mean, the moon's, radius of the moon's about a quarter of a degree. So we are talking a large section of the sky that we're mismatching. And so while that's not much of an issue for very wide field cameras, it can be an issue for people who are using 20 arc minute field of views or 10 arc minute field of views. So that could be the difference of predicting the satellite passing through the field of view or not. What makes things a bit more interesting and a bit more complicated is the TLEs are released every 8 hours. Here we've got from basically Space Tracker board, which is basically the latest space showing showing SpaceX ephemeris files. And ephemeris files are basically when you take the TLE, you use your orbital equations, and you get the ephemeris. So SpaceX does do this for us. I know OneWeb does, but I think that's not available publicly. It's only available to the operators. But the main thing here I want to show is basically that they're released roughly every 8 hours. So if you have potential orbital maneuvers taking place after the release of the TLE, there's potentially a solar storm or solar activity, which increases the temperature of the outer atmosphere, which increases the scale height, which increases the density, which increases the atmospheric drag. This can have an impact on the movement of the satellite and therefore can cause issues to accurately forecast where it's going to be at time X. And so the question is, how accurate are the TLEs when you propagate them into the future for only 1 hour compared to, say, 7 hours? So to do this, we need to actually start doing these measurements of the TLE accuracies at different locations on the Earth. Thankfully, because we have different longitudes, you have different time zones, and so if a TLE is being released at UTC -2, it'll be perfect. We might, just in time for the evening in the UK, it'll be perfect to get accuracies of less than an hour. That same TLE can then be used here in Chile about 3-4 hours later, and so we're able to measure the accuracy to about 3-4 hours after release. And so by having telescopes at different longitudes across the globe, we're actually able to measure the accuracy of the TLE as a function of time. And this will then aid in any development of any forecasting models and mitigation measures. So there's basically the observations we're doing, and they're the sort of observations that we need primarily at the moment. I mean, this is all changing. So in a couple of years, we might be needing completely different types of observations. So I just want to reintroduce SATOP again. It was basically supposed to be a one-stop shop for training, outreach, and collection and analysis of satellite observations. We're doing something similar here in Chile, but basically the impacts of satellites will not go away. This needs to be an international effort that affects everyone, all of us that enjoy the night sky. And so basically we need to work as an international team or international group, collaborate, to basically try and solve this issue as soon as possible for everyone involved. And basically the main thing is we need to quantify and monitor the impacts, because basically it's all well and good and saying I remember stories of people telling me about the iridium flares, it was the end of astronomy, and then it turned out it wasn't. It might be similar like that with these satellites for certain types of astronomy. But for other types of astronomy, like near-Earth objects, it's going to, ultra-wide fields, it's going to have a far more reaching impact. The situation is continually evolving with new types of satellites designs being launched, new mega constellations. And so we need to get data for all of these satellites for these new situations so we can actually adequately look into them. The other idea about SatHub is basically create a website hub and community to help compile all the data and tools, provide feedback with the operators, and also to help inform the community of what's going on. So basically, it's not just a case for to log in, to download some data, to do some analysis, or to upload some data. It's also providing tools to help people mitigate satellite constellations, and also provide feedback and for members of the community to see what's going on, how we're doing things, and how can they potentially help in the future. The whole idea of SatHub is basically for us, both observers, both professional and amateur, for satellite operators and space regulators. And by all of us working together, we can see the needs of each individual group and then work together to try and solve them to make the use of outer space for everyone. Very similar project that was mentioned to me was basically Project Moonwatch back from the 60s, where basically we got citizen science involved to help, for the watching of the moon. And also, I know myself and my own work in exoplanets, citizen science, detecting exoplanets in TESS data and public archives, and there's been quite a few exoplanets detected by citizen science. So getting everyone involved, not just the professionals or the amateurs, but also photographers, stargazers, people who do astrophotography, and anyone who basically wants to learn more. Part of SatHub is the Trailblazer project that's been led by Meredith's student and Dino, and basically they're building an open data repository for satellite streaked images. So basically how they're wanting it to be when it's up and running is that users can upload new data at any time after given vetted metadata, which I'll talk about in a bit. And users can access real representative data, fits files in minutes. So basically people who want to do all the data analysis and looking at models and so on and so forth. And eventually they want to have a situation where basically an astronomer can think, my otherwise perfectly good observations have these damn satellites in them, and I'll upload them to Trailblazer so it's not a total loss. And also basically for any groups who want to characterize the extent of satellite streak problems, but don't have access to telescopes collecting all this data, they can access all this data and actually start fitting their models and stuff, as I said before. Here in Chile, we're doing something very similar through CleoSat. Basically, we have a publicly available satellite tracking code available to help plan observations of Starlink and OneWeb satellites at our GitHub page. Again, it's written, as I said in my previous talk, it's written in Python, but it's been written in such a way that you don't need to code in Python. You just need to install Python, install the dependencies, and you can just run it from terminal saying, Python space satellite visibility. And it'll basically calculate all the visible satellites from your given location that you put in the input file. Currently, we've got work going on by our postdoc, Christian Adam, at the University of Antofagasta under an ESO regional funds grant, and our PhD student, Maria Isabel, who's at the University of Atacama with myself, being funded by the US Air Force Office of Scientific Research Grant. And basically, at the moment, they're working to develop a data pipeline to perform image calibrations, flats, bias, darks, and perform astrometric calibrations, and eventually automatic streak detection and measuring the magnitude of the satellites. We did all this by hand originally. I mean, our original work, basically, I selected, oh, that's a good comparison style, that's a good comparison style, that's the aperture, that's the aperture. Here's the satellite here and here at two ends, and then, do the analysis. However, when we're getting thousands, I think, last year we got 700 observations of Starlinks from Danish. We've now got over 1,000 observations from the telescope in Korea, and we're building up very large data sets. We don't have time to spend 15, 20 minutes per image to sit down and do it yourself. We need an automated partner to do it for us. And we hopefully, though, at some point to have the pipeline available to both the community through the ClearSat repository and via SatHub later this year, though I'm discussing this with Meredith, and we'll just see how we can integrate everything together at some point in the future. Okay, yeah, okay. Freaky. Okay, so the types of observations that we are needing. Basically, to ascertain the true impact of all the, to all areas of astronomy, we need accurate models, which require large amounts of data to help constrain satellite reflective properties and the parameters which govern them: range, phase, angles, orientation, or attitude. And to this, then, we're always looking for more data, and you can never have too much data. We're scientists, we love data. Because of this, SatHub aims to set up a data repository for astronomers to upload any data they have collected, both intentionally and accidentally. We're also doing the same with CleoSat, but basically the data repositories will provide researchers from around the world the data they need in their work without having to develop observing networks. I mean, it took us about 2 years to get about 5 telescopes on board, and obviously we're also looking for more telescopes, but these things take time. You have to sign agreements, you have to convince them that it's a good thing, and it's a filler project, it doesn't impact the main site. It still takes time. So it'll be sometimes a lot easier for a research group to say, hey, we got the codes to analyze all of this, we want the models to test, whereas, can we get this data for free? And yes, the idea is the data will be made available for free. As for the data format, ideally, we want to use FITS data, or flexible image transport system, basically to allow the measurement satellites to measure the satellite's reflectivity brightness, and astrometry to measure the TLE accuracy. However, this is also possible to do, though it's a bit more complicated with any more image formats, such as the negative, can't see it under my thing, sorry. Yeah, digital negative images, sorry. The ClearSat and SatHub data repositories will be designed to ingest multiple types of image formats, and even post-processed images are of value. So that's basically, you take an image to your camera and it gives you a PNG or a JPEG or a TIFF file. Basically, the raw image has been processed by the onboard, not the detector, but the computer under the detector, and it kind of skews things and makes it very difficult to actually get direct scientific information out. But all of these images are still usable. For example, measuring how many satellite streaks pass through the field of view in this number of minutes. This all helps us. And basically, we also ask to provide accurate metadata, such as location and timings of the images. So basically, if you've got GPS, you could say, I was at this location at this time, and we saw these numbers of satellites. And so that all helps fit into everything and allows us to actually do proper data analysis. For the TLE data, we don't need, for the magnitude measurements, we don't need the endpoints of the streaks. They can go from one edge to the other edge. That's fine for the magnitude. But if you want to measure the TLE, we ideally want to have both a start and end point of the satellite streak. However, if you only have one start and end point, we can still measure the accuracy of the TLE after we determine the direction of travel. As I said before, we know it's traveling plus RA negative deck. We can then look at the angle of the satellite streak and say, yeah, okay, it's moving from this end to this end, and we can still calculate it from there. However, we need still, like in this image, if there's no endpoints, we can't exactly say exactly which point in the 10 seconds the satellite was. However, we want to make this interactive, both for the professional and amateur communities. And so to build a suitable repository where everyone can upload and download the data requires input from both groups and what they want. As I said, as scientists, we would write FITS files. But in the amateur community, you might not used to be dealing with FITS files. So any data formats that you use generally, which are easy to use, please let us know. We can try and work out how we can use that data and perhaps even analyze that data if possible. And therefore we can integrate it into these data repositories. So it makes your life a lot easier. You're not having to go out and buy new equipment or new data analysis, data reading software. You can just upload what you already have with us. Okay, thank you ever so much.
Thank you very much, Jeremy. That's fabulous. Thank you very much. And I think we'll move on straight to Juliana's talk. And then if we've got any questions, perhaps we could leave all those to the end, to the Q&A session at the end. Can I please remind the people attending that this is what the Q&A session is for? Is there any of those little things you didn't quite understand, any of the things you'd like explained further, anything you'd like more information about, then please put them in the Q&A box so that we can discuss them then, even if it's not strictly a question, but something you just like hear a little bit more discussion about. Okay, Juliana, over to you.
Yes, I'm ready. Can you hear me?
Yes.
I will share my screen, just one moment. And okay, can you see it full screen?
Yes, perfectly. Thank you.
Perfect. Okay, so thank you very much, Paul, and my presentation will be on international law, national policy and industry perspective in satellite constellations. I am Giuliana Rotola. I'm a PhD student at the University of Sant'Anna in Pisa, and I'm working on climate change, sustainability, and the Earth space system, and how to find better practices for sustainable uses of outer space. So I will discuss a little bit what Connie mentioned before, the Dark and Quiet Skies report, and in particular what the Satellite Constellation Working Group did during the conference, and what were the conclusions of that working group. And I will address the international law framework and how astronomy fits into this framework, in particular looking at international space law, international environmental law, and the impact of satellite constellation not only on astronomy but also on society. And we can look at the international law recommendation, and then we'll go a little bit more deeply into what national policymakers and regulators could do. We'll look at the study the working group did on different countries around the world, what were the takeaways of this report, and then briefly also look at what are the recommendations for the industry and the best practices and priorities in the engagement between industry, astronomers, and other stakeholders in the use of the outer space and the sky. So the Dark and Quiet Skies for Science and Society Conference, Part 2 had 3 main working groups: artificial light at night, radio astronomy, and satellite constellation. So I was involved in all the SATCOM 1, SATCOM 2, Dark and Quiet Skies 1 and 2, and in particular for Dark and Quiet Skies 2, I was co-chairing with Andy Williams the Satellite Constellation Working Group. The working group covered 4 main areas. So we looked at international law and governance of outer space, national policy and regulation, industry engagement and collaboration with the astronomy community, with the representatives from most satellite operators now involved with the satellite constellations, and also astronomy and observatory requirements. So I will focus on the regulatory aspects of the first 3 points, as you already have heard many technical presentations in these days, and my areas of expertise is mostly on law and policy. So the first question we asked was if astronomy should be considered a space activity and therefore addressed in international fora like COPUS, so the Committee on the Peaceful Uses of Outer Space that both Piero and Connie mentioned before, that are fora that actually contributes to the creation and implementation of the international space law. And while the answer would simply seem yes, it is not always like that. So astronomy has not always been considered a space activity worthy of preservation under the Outer Space Treaty and in this international space fora. So we conducted a systematic review, interpretation of the Outer Space Treaty, looking at the ordinary meaning of the terms that were used in the treaty, the purpose and the context of the treaty, to understand what could be a definition of space activity, as the Outer Space Treaty itself doesn't provide a definition of it. So we looked at the interpretation of terms like exploration, use, scientific investigation, and concluded that there can be a broad interpretation for which astronomy can be seen as one of the oldest forms of exploration and use of outer space. So we also looked at practices of including astronomy and related areas in COPUS discussion. And we considered and all of those discussions that consider the importance of astronomy and the preservation of the sky to conduct scientific investigation, to reinforce the idea that astronomy should be addressed by COPUS. And luckily, our consideration were successful, because we had, as Piero mentioned, we had a discussion last year at the Scientific and Technical Subcommittee. It will happen again, but the process was not always so straight. So we looked at all of these previous examples of astronomy discussion at COPUS. One of the first was during the 3rd United Nations Conference on the Exploration and Peaceful Uses of Outer Space, Unispace 3, that happened in Vienna in 1999, where actions were proposed to protect the global and the space environment and guarantee equal access to space science and its benefits. Then a couple of years later, the IAU raised at Scopus the issue of space advertising that is actually very similar to what is happening with satellite constellation. And in that occasion, they observe how space advertising were imposing a qualitative change in the environmental condition for astronomy and causing a gradual loss in the possibility of observing a pristine sky. Then one of the most important acknowledgements of astronomy as a space activity is the establishment of the International Asteroid Warning Network, along with the Space Mission Advisory Group in 2014 by the UN Office for Outer Space Affairs. And then there are further reference in the Space 2030 agenda and its implementation plan, and finally also in the report of the 62nd session of Scopus, when discussing the legal aspects of space traffic management, were also included consideration on the impact of satellite constellation on astronomy. So in light of all of this consideration, the interpretation of specific terms, the previous discussion of astronomy at Scopus, we concluded that astronomy can be considered a form of exploration and use of outer space, and therefore it should be protected by the Outer Space Treaty provision and should be discussed further at Scopus. But of course, space law is just part of the broader system of international law. So we shouldn't be looking just at the Outer Space Treaty, but also and the related treaties that are governing the exploration and use of outer space, but also at all the sources of international law that can apply to the exploration and use of outer space, as it's stated in Article 3 of the Outer Space Treaty. So, of course, we don't apply the whole body of international law norms to outer space and to the issue of satellite constellation, but there are specific environmental norms that can apply, and I will discuss further what are those principles of environmental law and international law that can be considered in the governance of the low Earth orbit. So, looking at the first most important principle governing the activities of states in the exploration and use of outer space, once we have established that the legitimacy of astronomy as a form of exploration of outer space, we must also underline that both astronomy and satellite constellations constitute legitimate uses of outer space, because Article 1 of the Outer Space Treaty provides for the freedom of access, use, exploration, and scientific investigation in outer space. Of course, these freedoms are not absolute, and so it is important to find a balance between the legitimate uses of outer space. And to do so, we need to look at what are the principles that are limiting these freedoms defined by the Article 1 of the Outer Space Treaty. And one of the most important limitations to these freedoms is the non-appropriation principle that is elaborated by Article 2 of the Outer Space Treaty. So while the access to outer space is non-rivalrous, orbits that are closer to Earth are unique, and so there could be a rivalry use in the access to these orbits. And when any actor utilizes this orbit to the extent of current and proposed global constellations, it means that other actors simply cannot go there, cannot access those same orbits. And another point that we need to consider is that the activities in low Earth orbit are essentially uncoordinated. So the allocation of orbital slots currently work on a purely first-come, first-served basis. So, and any spacecraft that is not deorbited from this region may be there for decades or even for centuries. So this means that the cumulative effect of satellite constellations, their long-term occupations of specific orbits, the lack of coordination in the use of these orbits, and the lack of due regard could constitute a form of appropriation of outer space and should be investigated further by the international community. Under international law, another important point is that states are responsible for the activities of their nationals. So Article 6 of the Outer Space Treaty requires that at least one state authorize and supervise its non-governmental entities and assure their continuing compliance with international law. So this requirement of continuous supervision that is stipulated in the second sentence of Article 6 of the Outer Space Treaty would imply that the state governments maintain this continuing supervision of over the space activities of its private actors, with the need to regulate all of the aspects related to the launch and the placement of the satellites, the operation of such satellites in Earth orbit, including their impacts in the outer space environment, and the orbit and end of mission life. But while studying different regulations in these different conferences, SATCOM 1, SATCOM 2, and Dark and Quiet Skies 1 and 2, we realized that there is actually a missing gap in the fact that in most of the regulation, national regulations, there is no consideration of protection according to the on-orbit operational phase of satellite constellations. So most of the regulations deal with the launching phase and the end of mission phase, but most regulations do not look at the on-orbital operation phase. So there is a need to regulate these additional aspects due to the impact of the increasing number of satellites. Then going further in the Outer Space Treaty, we find another important limitation to the freedoms of Article 1 in Article 9 of the Outer Space Treaty, that provides for obligation of due regards, prevention of harmful interference, and obligations to engage in international consultations in the case of potential harmful interference. So I've already discussed the idea of considering astronomy as a space activity, and actually the need to consider astronomy as a space activity derives exactly from the potential use of these forms of protection for astronomical observation. And there is one important historical precedent that support the idea of including ground-based astronomical observation in the activities that needs to be taken into account when carrying out activities in outer space. So it is the Westport experiment that involved the launch and the release of millions of copper needles into the low Earth orbit for the purpose of creating an artificial belt around the Earth. And on that occasion, astronomers worldwide complained that the experiment had the potential to cause interference that would ruin their radio and optical observations of the sky. And due to this criticism, there was an agreement reached in 1963 on a recommendation that was directed at the attention of COPUS to the urgency and importance of the problem of preventing potentially harmful interference with peaceful uses of outer space. So we can conclude that the states parties have to pay due regard to the corresponding interests of other states that will be affected by the light and radio pollution created by satellite constellations. Specifically for non-governmental activities, states should adopt the licensing conditions that take into account the impact of those constellations on ground-based astronomy, and I will discuss a little bit more this in the national policy part of my presentation. But in general, there should be forms of obligation to consult with potentially affected state parties that includes consideration on all the affected stakeholders, including astronomy, both for ground-based astronomy and space-based astronomy. And in this, we also need to look at the role of private entities, because I mentioned that states are mostly responsible for their activities, and in general, obligations of international law are not directed at private actors, but still there is a role that private entities can play in this preservation of the outer space environment. So with our working group, we looked at the concept of corporate social responsibility, environmental protection in outer space, and all the current developments in this area, in particular to identify all the objectives of private entities in paying due regard for the stakeholders' interest, including issues such as human rights and environmental pollution, and mitigating the corporate and financial risk of current and potentially unsustainable practices. One current example in this trend is the space sustainability rating. That is a concept developed by the World Economic Forum, and it aims to promote mission design and operational concepts that avoid an unhampered growth in space debris. And it promotes a future where actually environmental review would be taken into consideration at the early stage of design and development of spacecraft. So those proposed by the Space Sustainability Rating are just voluntary measures, but still are a good step in the direction of promoting a more sustainable use of space, also at the private corporate level. Now, I want to turn for a moment into environmental considerations, because I mentioned at the start that, of course, not only space law can be applicable to space, but also some other part of branch of international law can apply. So in general, we can say that the environment is generally understood in relation to the human quality of life. And LEO, which is a potentially natural limited resources, is today key for the quality of life for humankind. So on one side, environmental law has often considered outer space within the scope of application. So we have seen conventions like the Rio Declaration looking at not only at the environment on Earth, but also at areas beyond the jurisdiction of states. And also the analysis of state practice before the outer space treaty shows that the free use of outer space has always been considered contingent upon its environmental protection. So in light of this consideration, we must look at some of the principles of environmental law that should apply to outer space, and in particular to low Earth orbit. Some of the principles are, for example, the prevention of transboundary harm that impose obligations on states to take all the appropriate measures to prevent damage or minimize risks. Then the precautionary principle that is included in the declaration that I mentioned, the Rio Declaration on Environment and Development, which implies that if there is a threat, the magnitude of which cannot yet be certain, then it is still necessary to take action to eliminate this threat. Another principle of environmental law that is applicable to the current context is the polluter pays principle, that is stating that the producer of a certain damage, so the polluter, must pay compensation for it. And finally, the principle of sustainable use supports the use of any resource in such a way that it prevents its rapid depletion, leading to extinction of this resource. And finally, I think for the international perspective, we can also look at the societal impact of satellite constellation, because of course astronomy is just one of the areas that are affected by these activities. So there could be a permanent loss of practicable scientific astronomy to global amateur and developing communities, and the importance of art related to the observation of the sky and astrophotography shouldn't be underestimated. Moreover, the loss of access to science and dark skies could have an unequal and underrepresented consequence for a different global range of societal stakeholders. So it's time to recognize as stakeholders of the sky, not only the usual ones or astronomers, governments, satellite operators, but all of the communities involved. So the preliminary conclusion for the international law perspective are that we should consider satellite constellations and astronomy as a legitimate form of accessing outer space. We should coordinate in the exercise of these activities, and an important role is those of states that must assess compliance with applicable law and must supervise the activities of their nationals. And in providing guidance for national activities, we also decided to look at the national policy and the regulatory system. So this working group look at what policymakers and regulators at the national level could do to implement the recommendations that we provided for in the Dark and Quiet Sky 1 report, and to consider all the regulatory solutions for the impact of satellite constellations. So the working group decided to organize this work around a framework that was highlighting the intent, the ultimate intent behind any regulatory solution. So we look at policies to avoid, which means all the policies and instruments that needs to avoid the effects on astronomy, either before the launch or once the satellite systems are already launched. Then also at policies and instruments to reduce the impact of effects that occur and are not preventable. And finally, at policies and instruments to prevent the occurrence of astronomy impact, establish the condition for dialogue and exchange of information, and achieve government policy coherence. To do so, we looked at the number of countries that we selected for our case studies, and the ambition was to ensure a diversity in the sample that we used for the diversity also in the different stages in the development of the space activities, the space economy and policy system of the countries that we analyzed. And for each of these countries, we looked at the licensing regulations, the law and policy that were including astronomy and environmental protection, the existence of bodies representing the scientific community, the implementation of international standards and best practices, and the existence in those countries of satellite constellation. I won't go into detail of all of the case studies, but you all can have a look at the report. Where all the single national case studies are included. But our main takeaways for the national perspective, so our main recommendation at the national level are the following. So the first thing that we identify is that in many cases, national space policies and strategies cater to the growth of the space economy and the support of the space industry and the commercial activities. So in many policies, there is an evident need for this balancing the economic growth of the country and the environmental concerns. And for this reason, it's important to not forget still the importance of the environmental assessment and ensure that the impact on astronomy are included in this environmental assessment. Then also we realized that many countries run astronomical programs, and still often astronomy is not represented in space policy discussion. So there is the need to updating this conceptualization of space activities and outer space and find really a role for astronomy in the field of space, recognize the importance of space as an environment, and understand better the functioning of low Earth orbit. Then the case studies demonstrated that emerging space nations are attentive to the practices and the policies of established space nations. So it's important, especially for emerging countries, echoing international behaviors, but also for those countries that are paving the way. It's important to creating leverages to include the issue of the impact of satellite activities, of space activities and satellite constellations on astronomy and on the dark sky. Then guiding and making private actors responsible and accountable is one of the most important things, and some countries lack a clear and detailed framework and mechanism to guide such private endeavors. So it's important to understand how to operate and to show private operators how to operate with sustainability and environmental concerns in mind. Then it is important to create strong synergies between the astronomical community, the industry, and the government, but also optimizing mechanism, because there is a need to create a clear and independent national space policies that are separated from the existing ones of other ministries, because often space policies are mixed with defense, science and technology, knowledge and innovation, and this creates a sort of fragmentation at the national level and confusion in what the policy for the preservation of the sky should be. And finally, involving citizens in the understanding of scientific and space programs is also very important, and the importance of governments of investing in space should be recognized and should be made more accessible to the general public. Finally, our working group on the industry that was, as Connie mentioned, coordinated by Chris from Amazon, at the objective of understanding how the international astronomy community can coordinate with the industry stakeholders and so mitigate the impacts and raise awareness and promote mutual interest of satellite operators and astronomers. The preliminary conclusion were that it's more likely that operators will adopt voluntary practices or mitigation tools if those are identified in the early project in early project stage. And to this end, we identified some of the best practices for the industry, and you can look at the guideline in the report, but in general we looked at how to address the visible brightness of around the visibility, address the visibility impact on astronomical science of large constellation, provide access to public data on individual satellites and constellation, providing more information or orbit tracing and the orbit consideration, and continue this collaboration between observations, satellite communities, operators, and astronomers. So to conclude, that the international law, we emphasize the importance of discussing astronomy international fora and the implementation of regulatory tools that exist but needs to be implemented at the final stage by states that are responsible for supervising national activities and implementing these norms. Then at the national level, it's important the inclusion of impact assessment in licensing process and ensuring internal policy coherence and external international collaboration. And finally, for the industry, it's critical the continuous engagement with astronomers and all the affected stakeholders. So thank you very much, and I hope I didn't go too much over time.
That's fine, Juliana. Thank you very much. We were running a couple of minutes late anyway. One of the things that occurs to me, of course, is that we have this disconnect between the time it takes for industry to do things. They can do things on the scale of months, if not a few years. Governments take perhaps a few years to a decade to do something. Whereas when you're talking about international treaties and getting things in place, you're literally talking about decades, maybe a couple of decades to get something in place. How do you address those sorts of problems? Because you're going to have maverick billionaires able to go out. They may be geniuses, they may have some great ideas, but they can put things in place without having law there to perhaps prevent them from doing it. The same arguments apply to, for example, discussions on artificial intelligence and things like that.
Yeah, I totally agree. Like the time in which these things happen, it's very different, and that's why like all of those recommendations, all of those actions should just go in parallel. We shouldn't wait for operators to have national regulations. We shouldn't wait to have an international treaty for the preservation of the sky or for the preservation of astronomy. We must start working in parallel, because for sure we need international regulations that can be applicable for the decades to come and can be applicable for operators that are coming in 10 years from now, 20 years from now. At the same time, we still need to make sure that we are discussing with the industry, and the industry know what are the best practices that also make them good actors in the use of outer space. I mean, being a good actor is always also a market value, so it's also in the interest of satellite operators to act in the best possible way when there is this uncertainty of policies. And we have seen that cooperating, bringing together satellite operators, astronomers, policymakers can actually work to make sure that there is a balance in the interest and in the access to outer space. But yes, we shouldn't. We cannot just wait for international law to work first, because as you mentioned, it is just too late. For the Outer Space Treaty, it took decades. If you think about the long-term sustainability guidelines, it took almost 20 years to approve something that is not even mandatory yet. So we need to rely on discussion like this, on the discussion like those that are happening and happen with the Dark and Quiet Skies conference, and that will happen with the IAU Center, to make sure that all of this process work in parallel, and we will have best practices on the industry, we will have international norms, and we will have national systems that are taking care of all of these aspects. But we need to raise awareness, we need discussion, and that's why I think the work that the IAU is doing and the center is extremely important in this stage.
Thank you. I've got a question here from Kate Mullard. She asks, is there legal consideration and provision of security for the ethnic groups we heard about yesterday that use the sky as part of their everyday? I know you touched on it very briefly in one of your bullet points. Could you say a little more about how ethnic groups are being involved?
So I was not part of the community engagement working group, but for sure there is during the SATCOM2 conference there were the community engagement team that addressed different communities. From our legal perspectives, we looked at all of those treaties that are looking at human rights preservation and human rights protection of, for example, of human rights of indigenous communities and the value of the outer space and dark skies for those communities. Of course, this is a long process because we cannot just assume that all of the communities think and work in the same way, and we cannot think that, for example, indigenous communities are just a monolith all around the world. So it's a process that will also require time, and I'm sure that it will also happen within the IAU Center. And yes, if Jessica or John are here, they can also present a little bit more of the results on the community engagement. But I think, yes, it will be a long process because it's important to recognize all of the different interests also within the different indigenous communities affected by the satellite constellations.
Thank you. There's a question here from, or a hand up from Piero.
Oh, I just wanted to add a comment about this because obviously we would all like to see regulation that defend the visibility of the sky, also in terms of the community that see the sky as an essential part of their life. And we will certainly, with the center, highlight to the world those community needs for the having a clear vision and a pristine view of the night sky. However, it's very frustrating to work at the UN regulation level because any regulation there has to be achieved by consensus. And with my experience in participating in this meeting, you can have endless discussion on a single word of a report because some delegation do not agree on an adjective or a word. And if there is no consensus, the document doesn't go on. So it's very painful in a sense for people who work in a different speed. But we have to go along that way. But we have to be conscious that it is extremely difficult, and because there are so many interests there, and some are interests that can be expressed, some other will not be expressed. Like there are military interest in the use of the space, and whenever you propose a regulation that touch on those interests, then you get to stop. And as Juliana mentioned, it took almost 10 years to get a long-term sustainability document, which is still being discussed and is not finalized. So we, as astronomers, we will concentrate on the protection of the astronomical sky. We know that the constellations are creating a lot more of issues that has to be taken care by the other entities like space agencies. So we will join in there proposing regulation, but we have to be ready to see this coming in very slowly, unfortunately. And so we will go along these two parallel lines, one in implementing the center and in engaging the industry and companies in working together to mitigate the effect of the constellation, hoping that this is a viable path. And in parallel, we will continue to push for regulation, but that will take much longer. So we have to move faster on finding our own solutions.
Thank you, Pierre. You have a comment, Andy?
Well, it's about existing environmental regulations. I just wanted to make a point that, as I think most of you will know, I got involved in this US Court of Appeals case, Viasat and the US Federal Communications Commission, with the point of that being that the FCC have always claimed they have a categorical exclusion, and that the existing act in the US does not apply to them, and the case is that it should do. So I just wanted to mention that that's been dragging on for quite a while, as you know, but what I understand is that there probably will be a decision on that in the next few weeks, because basically the US Court of Appeals goes into summer recession soon. So either it is in the next few weeks or it's going to be a long time yet. But I just feel that that case might be set an important precedent for existing environmental regulations to apply.
Yeah,
I think
I totally agree.
sorry, Juliana. Go.
No, yeah, we discussed also a little bit the case, and I'm following it. The problem with the US is probably that I think in general in the regulation they do not recognize, or until now, the outer space environment as part of the system of Earth, and this is a sort of excuse for not thinking that the environmental consideration should be applicable to outer space. So this is also part of my PhD research. I'm trying to make sure that the outer space environment is considered as part of a unique system also with Earth. We cannot just consider Earth as one thing and space as another thing and the moon as another thing. We are all part of the same system, and to this we need to take care of this unique same system and apply principle of environmental sustainability and transdimensional realms and all of these principles that I mentioned before, and even more. But yes, it's very difficult at the US level. So we'll see how the decision of the Court of Appeal will go. I hope it will be a good precedent for the application of environmental norms also to outer space.
Well, so I just thought, in particular, it answers a potentially Paul's timescale worry. You know, that there are regulations, and so the starting point's got to be use them. I think, because new regulations will take a long time.
And of course, the more we use, and of course, the more time it buys us to get other regulations examined, reviewed, and perhaps put in place. And one of the things I was going to say, of course, is that at the moment, SpaceX are having difficulties with the FAA in Boca Chica, because they've built their starbase there right next to a wildlife reserve, as well as a military monument, and they're now being challenged on the use of the access road past the monument and going out to the beach, which is a public beach, and complaints that the road will have to be closed much too often to withhold the beach from people's use and the access to the monument and the visitor center from people's use. Plus, of course, the launches are affecting the bird life, and there are some mud flats there and all of those sorts of things that are sites of special scientific interest, or whatever the US equivalent is. And so now the investigation that the FAA has called, and they called for public comment, it's now been delayed, I think 3 times, with the end of May now being the time for the report as to whether they can continue to launch from the base at Boca Chica. So already there are environmental concerns coming to the fore that are not letting the operators get their own way entirely. I've got a question down here. This is Roberto Casalegno saying, don't you think the proposed regulation recommendations are coming a little late in respect of the actual development of constellations? Is there still room for coordinate actors, public and private? I guess this is it too late type of question.
It is a bit too late. I mean, it's crazy if you think that this issue in different forms has been reproposed through the decades. So we have seen the Westport case in the 60s, and then early 2000 we had the space advertising, and now we have satellite constellations, and still we don't have proper adequate solutions for the preservation of astronomy. So yes, these regulations are coming a little bit too late. but we must make sure that we have international law that can be applicable to these cases. We have environmental regulations that can be applicable to these places. So we don't need to reinvent the wheel. We can use what we already have. We just must make sure that the international community is aware of this issue, that astronomers are considered part of the stakeholders of the sky. Because what I mentioned before, even in the national case studies, we see that astronomers or astronomy is not even considered as part of the space activities of a specific country. So we must make sure that even if it is conducted from the ground, we are using the sky. We are stakeholders. We as astronomers, let's say, stakeholders in the use of the sky. And once we recognize that, we can make sure that the existing regulations and existing norms are applied for the protection of the sky. We cannot wait anymore 60 years. And what happened with Westward and space advertising and Constellations now needs to find a space is so crowded.
Okay, thank you very much, Juliana. We missed, I think, a little bit, or I missed a little bit with the connection there, but thank you very much, and thank you, Piero, for your presence. I believe you have to go now. Perhaps we could move on now to the more general part of the Q&A, and I have a comment here to Connie. In response to a question that was asked by Steve Tonkin about SatHub. In fact, the FAS in the UK and the British Astronomical Association and the Society for Popular Astronomy have formed a group where we are seeking to coordinate the amateurs in the UK to take part in an observing project, to collaborate and contribute to something like SatHub. We started about 18 months ago, which was perhaps too early in the sense that we didn't want to start and to try and get our members enthused and observing and so on, only to find that the data didn't fit in with what was going to be generally more acceptable to a larger collaborative effort. So we've made some approaches to Meredith Rawls, and we've had Harry Krantz appear in one of our meetings, one of our Zoom meetings. But certainly I think the FAS that's coordinating this would like very much to be a part of the collaborative contributor to the project and in SatHub. And I think that may, to some extent, answer Steve's question, is that there will be things going on in the UK, and the FAS is, as I say, coordinating. We're not leading, but we're calling the meetings and bringing people together. So I hope that will help.
Well, that is excellent. We'd be crazy not to have you guys as part of our membership. And so, yes, we will welcome that. And I'll talk more with Meredith. There will be a data repository in which both amateurs, astronomers, and professional astronomers can deposit their imagery and any metadata information that they need to also deposit. And I think it'll be in a number of different formats. We prefer FITs, but you know, that's not always possible, especially with amateur astronomy data. So yes, that'll be available as well. And keep in tune with us when we have our website available with all this sort of information on it. It will be cps.iau.org, I believe, when it goes live. So and feel free to always email any one of us, and also Meredith. I'll put her on the spot as well. Thank you.
Yes. Okay. I've got a question here from Charles. Is Charles in as an attendee or as a panelist? I'll just put Charles, promote Charles to being a panelist, if that's okay. And then
well, we always welcome Charles.
Yes. So Charles, would you like to put the question here? You asked about, you might have had a comment for Andy.
Yes, Andy, as I mentioned in the comment, I appreciate your optimism on the Viasat and FCC litigation. and I await the decision of the Court of Appeals. What my fear is, what happens if the Court of Appeals affirms the FCC's position that it's the scope of NEPA and the Council on Environmental Quality, or Council on Environmental Quality regulations, only apply to terrestrial operations and conduct, and what's the backup plan? Where do you see us going from there if that occurs?
A very good question. Yeah, it is a serious risk, and I think that's part of the reason why, when doing this, I would discuss the amicus brief, as you know, with a lot of other people, and basically it was me that stuck my head above the parapet, partly because people didn't want to spoil their relationship with SpaceX, I think, but also because of exactly this reason. I think some people were worried whether the timing was right. And my feeling was that it was happening anyway, so it ought to be supported, and basically nothing ventured, nothing gained. But the risk has always been there that it could be a setback if the ruling is against. An even better point is your question of whether there's a backup plan. So I don't have one, but I think we have to regroup. And I think the feeling, as expressed in Juliana's talk and in the paper that a whole bunch of us put together for Nature recently, and the long-standing tradition of Moriba and others, the kind of groundswell for the idea of space and environment, and that including astronomy, is very strong. And at the end of the day, I think you don't invent regulations and try and make people behave. Regulations emerge from culture, I believe. So I'm still medium to long term optimistic, even if that specific decision gets knocked back, because I think the momentum is fairly clear, and including it's starting to be noticed by the media, for instance. So
right.
People know it's an issue, and when this gets discussed on sort of Twitter and Facebook and whatever, it's clear that not all the public agree. Some of the public are going, no, you're making a fuss, it's just more vested interests, etc. But actually, an awful lot of people have sort of recognized this and sprung into it, and that's what's going to matter at the end of the day. I think it's it's the public interest and media attention, and at the same time, as I think as Juliana said this, we've got to pursue parallel tracks.
Right.
So you've got to be having the conversations at COPUOS at the same time as making a public fuss and pursuing law cases and so on. So I'm aware I'm not quite answering your question, because I don't personally have a backup plan apart from try again, regroup, because I think the momentum is there.
Yeah, and I think you have answered the question, and the question that I asked you is oftentimes asked of me, where I have been advocating that we need to propose amendments to NEPA and the Council on Environmental Quality regulations to make it explicit that Earth's orbital space is included within Earth's environment. And the question is, well, if you're pushing for that clarification, aren't you suggesting that NEPA does not already include the orbital space? And my response is no. It's the two can be consistent. One, there's an ambiguity, and everybody can argue their positions on the ambiguity. The other is, all right, with that ambiguity, let's try to eliminate the ambiguity and make it clearer what already exists. So the two arguments can be aligned. They're not contradictory with one another. And I think that goes to your point, in that, if the ruling is positive, it's fantastic because it catapults us forward in terms of the arguments that can be made with the FCC. And if it's not, then it drives home the point that we do need to, and one final comment is on your latter point in the public awareness, then that can be a catapult or a catalyst for the public to realize that there isn't something that addresses that right now. And the FCC apparently has a pass to do whatever it wants because it thinks that once it's out of orbit, they don't need to worry about it.
So,
but I appreciate your answer.
Yeah, let me just pick up two things there. One is that I think I'm actually quite jealous of the US situation in NEPA, because I think in NEPA, you've got a particularly simple, all-encompassing piece of regulation that applies to any federal agency in principle. Whereas I don't know about other countries, but in the UK, it's much more diffuse. I mean, you know, there's some environmental regulation about this and environmental regulation about this, and there isn't a single point of focus the way there is with NEPA. So again, I think NEPA is a great opportunity. The other thing I wanted to add is that in terms of what the ruling might be, I found myself wondering whether if the judges were wise, you know, they might say, well, you know, this in principle, officially, this is an appeal against the license revision that was being considered, which involved, you know, orbit lowering and so on. And we don't think it's right to revoke that decision and make you do an environmental impact assessment on that. But we do think you know there should be environmental impact assessment for major future things, such as, for instance, the Starlink Generation 2, you know, plus 30,000. That I think would be a fairly sane decision. So that's what I'm kind of crossing my fingers on. But
right.
but who knows?
Great, thank you.
Thank you. Perhaps I think we're coming towards the end. Perhaps I could just ask one more question here, which I think probably best aimed initially at Connie, from Doug Edworthy. He says, I appreciate that much new knowledge has been attained in the last few years, but how much telescope time and the time of astronomical professionals has been spent on the subject of mega-constellations, time that could otherwise have been devoted to astronomical research?
Yes, that was one of our first fears, actually, when we all started this a couple of years back. We thought, oh my goodness, the time we have to spend on trying to figure out what the issues are, what the mitigation solutions are, and the money, the funding that we'll need with which to do this to some ends that could make a difference is just astronomical, basically, and how that would take away from, say, postdocs doing research that they could, you know, otherwise on other mainstream topics of astronomy. So we have not, I mean, there's been estimates, but it's not really conclusive at this point. We're still, as Piero said earlier, in answer to a similar question, we are going to definitely have that as part of our venue of what we do in the IAU Center. But it's I mean, when you think about, let me see, the Rubin Observatory, I think is something like 743, or is it 473? I can't remember, $1 million or more to get that running. You know, and then they think that maybe up to a year, you have to go longer than the 10 years it's going to have in terms of its lifetime, just because it has to mitigate the impact on satellite constellations. I mean, that's 10% more cost right there, just for one telescope, right? So when you consider that kind of impact, and then it's going to be different for different telescopes and different situations. And then, of course, as was already touched upon too, the solutions, you know, all the software that you have to create, and hopefully a lot of that generic stuff will be through the Sat Hub in the center, and then carry forward to other institutions, and they can tweak on it to, you know, and that's going to take time for them to tweak on it to be specific to their needs at their telescope. So it's just, it's astronomical, really, truly astronomical, and considering impact it's going to have cost-wise and people-wise, and how that does take away from other types of research. Because, you know, in the US, for instance, only so much money goes to the astronomical sciences.
Yes, yes. Jeremy, you've got a comment?
So yes, I mean, obviously I can only talk about from my own perspective and anecdotal evidence. But for example, my last publication in the actual exoplanets was January last year. So that's the last time I actually done any exoplanet work, and hopefully July I'll be able to get some done. But in terms of funding and that, yeah, we've been very quite successful in getting funding for this sort of research. And I went through a cost calculation, including indirect costs for the university. We've been awarded about just under $500,000 US for the next 3 years. Okay, that's not per year, that's over the 3 years. But that's $500,000 that could have gone to postdocs and students doing black holes, quasars, you know, other astronomy. So, you know, that's money coming from the public purse, so it's been diverted. But I mean, it's good to help us try and sort out the situation, but that's less money for science.
Yes. Are you there, Olivier? If you're able to comment, roughly what proportion of your time would you say has been taken?
For me, it's not that much. A couple of months.
For all of the work you've done?
Yes.
You work very fast.
No, it's really, I mean, I'm a bad example in the sense that it has been, yeah, I would say 1 month full time and another month full time.
Yes.
So it's not representative of the overall effort.
Yes. Okay, I thank you, everyone. All good things must come to an end. I think this has been a really good, really interesting couple of days. And I must thank all of the speakers whose arms I twisted and incessant emails, with my emails playing up. And we managed to pull together a very good program, a very good set of talks. And I think we've had a lot of very interested people who hopefully will benefit very much from all of the work that's gone into this and the talks that have been given. Just to put in a slight plug, I'm starting to plan another webinar for the FAS, which will be in July the 18th, I think it is, on pro-am collaboration in astronomy. So that'll be just a 1 day webinar. So that's another one on the books. Okay, and thanks to my wingman here, Martin, who's been working behind the scenes, pedaling hard with his feet under the water, making sure that slides get put up and videos get played and things like that. And thank you also to all of the people who have participated and have as attendees. And thank you all very much. And I hope that you've all found it of great benefit. Thank you again to everybody. Thank you.
Goodbye.